Okay, good. All right, great. Thank you, Maggie. All right. Um, Good morning. Welcome back. We're well into the magnetosphere today. Um, we've got Christine Gabrielse, who I remember as an undergraduate. And now she's a lecturer at the Heliophysics Summer School. And Slava Merkin, on tap today, talking about the magnetosphere data and the magnetosphere modeling. And so, Mark, who's moderating today? Do you have that list?
I'll find it, and it is.
Yeah, I believe it's Mark.
Or Maggie.
Yeah,
okay. Yep.
Mark today.
So so Christine, I'll monitor the chat for you and interrupt if there's any questions, so you don't have to try to balance too many things.
Thanks, Mark. I actually was worried about that, so I have two devices going on
awesome.
now so that I could see the chat, but having your help would be even better, so thank you.
Great.
Should I go ahead then?
Sounds good, unless Nick, you have any other
I don't
updates?
think we have no housekeeping.
Okay, great. So if you could introduce yourself and let the HSS students know about some of the work you're doing.
Okay, sure. Hi, everyone. As Nick mentioned, my name is Christine Gabrielse, and I work at the Aerospace Corporation, which is in El Segundo, California, the greater Los Angeles area. Before that, I was at UCLA. I did my PhD there studying substorms and particle injections in the magnetotail, and my work has branched from that to also include precipitation into the ionosphere and how that results in aurora, and how, I guess you could in one sentence say, I study how the energy flows throughout the magnetotail and into the ionosphere. And just the Aerospace Corporation is not a university, like probably some of your lecturers have been professors. It's actually a nonprofit that supports various U.S. Institutions like NASA, NSF, the DoD. So that's kind of me in a nutshell. And I was very excited to be able to come lecture to you today about the magnetosphere from a data perspective. And as an overview, I was thinking, wow, there's so much cool stuff and so little time. So how do I put this lecture together? How do you cover the magnetosphere in 2 50-minute lectures? So I decided to focus it on convection and substorms specifically, since I have some background in that myself. And just as a caveat, I say even so, there's a lot of material on convection and substorms. So I'll cover as much as I can, and I try to focus it by looking at each other through the lens of the other. So the goal today is to make convection and substorm concepts accessible to a grad student audience. I know that you all come in with various degrees of education, so we'll try and step in at a pretty early level. So for some of you, this may be review, but hopefully it's still helpful, and maybe some of you will be seeing it for the first time. And so we'll start with some theory, but we'll then move on to use some recent studies as examples to demonstrate current works in the field and how data is used to study these concepts. So we'll go over some introductory material, like the Dungy cycle. I call it particle motion light because we won't go into it in super depth in just 1 or 2 lectures, but we'll touch on it so we can understand how particles move in the magnetosphere. We'll talk about convection on large scales, but even more so on mesoscales, which we'll define later, and specifically how it relates to substorms. First, I need to make this little floating panel disappear so that I can see the screen. There we go. All right, so convection, the Dungy cycle. This is about magnetic flux transport from the day side to the night side and back. And in a steady state, all these rates must be equal. And when we're talking about magnetic flux, we're talking about the amount of magnetic field within an area at some angle that coming out of that piece of area. So this is the famous Dungy figure from a very short letter. It's less than 2 pages, and yet it's been cited thousands of times in our field. So it's very important to the magnetosphere and how it works. I think you have already talked about the solar wind and the IMF in earlier lectures. So this should be a transition into the magnetosphere. Now, when you have the solar wind can have a southward component, which we see the vector here pointing downward. And when it has a southward component, it can reconnect with Earth's magnetic field, which when it's coming out from the South Pole, and then you can see the vectors, it's facing northward and then going into the North Pole. And so when these two magnetic fields are pointing the opposite direction, they can reconnect. And then the solar wind is connected to the Earth's magnetic field, pulling it backwards into the tail and creating the magnetotail until it can actually reconnect in the tail as well. And then comes cycling back to the day side. And so that is the Dungy cycle in a nutshell. Now this convection also occurs when the IMF is northward. It just doesn't reconnect here at the nose of the magnetosphere. It reconnects farther back in the tail, but convection still happens. And when it's northward like this, it's a bit more of that steady state than when it's southward, and then that's when we get our more active substorm times, which we'll get into later. But first, to look more at convection on a more global scale, these magnetic field lines are reconnecting here on the nose and being dragged back into the tail. You can see that their foot point in the ionosphere, so the foot point is where the magnetic field line connects to Earth in the ionosphere, is being dragged back towards the night side. And that creates plasma flows in the ionosphere. And so you can see that it creates flows like this in this sketch going tailward. And then as they come back to the day side again, then you see those field line, the flows coming back to the day side like that. And you can read more about this if you have the Kivelson and Russell Space Plasma Physics book. So how do we know about all this? Well, we can observe this with data, since that's the topic of this lectures. These particular figures here are created using super darn radar. So these radar are on the surface of the Earth, and they're looking up into the ionosphere, and they can measure the speed of the plasma flow in the ionosphere. These plots have also been made with satellites that could also measure the flow speed of the ionosphere. And what we're seeing here are different contours or equipotentials. These are also contours of motion of the plasma according to what we call the IMF clock angle, which means just each arrow is pointing to tell you what direction is the IMF pointing. So in this top center one, that would mean the IMF is completely pointing in the positive BZ direction. And pointing down, it's pointing completely in the negative BZ direction. And on the sides, that means there's a BY component. So on the right, it's all in the positive Y. On the left, it's all in the negative Y. And you can see that, again, kind of what we talked about in the last slide, when you have a positive BZ, the convection is steady, but it's not so strong. and you can see that this very weak 2-cell convection here. But when you have a negative BZ and day-side reconnection that's then really driving that convection, you have a very strong, what we call 2-cell convection pattern here, where we have plasma moving towards the night side in the center here and then recirculating back to the day side. And so the two sides, this side and this side, are just done in the two hemispheres of Earth, which is interesting to study because you can see different asymmetries between the northern and southern hemisphere and how all of this works together. So you have a lot of references here if you want to read more about it on your own time. So this is just to kind of explain a cool, what I think is kind of cool. As you have the convection occurring over the polar cap. So here is just a drawing of that, where here we're seeing, this is the day side, this is the night side. The plasma is moving towards the night side. And as it's moving towards the night side, you see this electric field forming. So electric field is equal to this flux over the distance, the diameter of the polar cap, or sorry, potential, I said flux, potential over the distance. Electric field is also equal to negative V cross B. So you have a velocity going across the polar cap, and you have a magnetic field going into the ionosphere. So that negative V cross B creates an electric field pointing in the westward direction across the polar cap. So you can use what we know. So the radius of the polar cap is 0.2 RE. The velocity of the plasma across the polar cap, let's say it's 330 meters per second. We knew the magnetic field in the polar cap is about 62,000 nanotesla. And so then plugging all that into this equation and solving for the potential, you get 52 kilovolts is the potential across the polar cap. So then what I think is kind of cool is you can actually calculate what is the electric field across the tail. And this has to do with convection, I promise you. So you use the same equation, the potential divided by 2 times the radius of the tail, which we know is about 20 RE. And then solving for the electric field by plugging in the potential from the polar cap, you get 0.2 millivolts per meter. And that is approximately what you will see the electric field is across the tail, which is perpendicular to these arrows you see. These arrows are the direction of the plasma motion as it's the plasma is heading back towards Earth. And that is what you see during a quiet time, more or less, meaning when not during a birth debulk flow, but during which we'll talk about later, sorry, during just the average convection period. Okay, so now we're going to go into what I call particle motion light, which again, some of you may have seen before, but it's always good to have a refresher because this also helps us understand the data that we observe. And since this Heliophysics School is about how models work with data, this is also a very important concept to our modeling. So we're going to be talking about guiding center equations of motion. And guiding center means in a background magnetic field, which in our case is pointing out of the screen, you're going to have electrons going in a circle, which you can use your right hand rule for. And I don't know if you can see me or not, but you just use your right hand rule to point your thumb in the direction of the magnetic field and then curl your fingers. And that curl of your fingers is the direction that the electrons gyrate. And ions are the opposite direction. So you just switch the direction that your fingers are pointing. And so what we're talking about is the center of this motion. What direction does that move? And that's the guiding center of motion. So the first case we're going to talk about is E cross B drift. So you have a magnetic field pointing out of your screen, an electric field pointing down on the screen. The equation, and this is why I say light, because I don't have time to derive these equations. I noticed in your textbook that the Heliophysics Summer School provided, it does go over particle motion equations. And also I suggest this Northrop 1963 paper, which goes through the derivations, and I find it easy to follow. But we'll just be looking at the final product to kind of get more of a conceptual understanding. So I would kind of like you all to take some time now looking at this equation. So this is the guiding center velocity of E cross B drift. And think about if you have a magnetic field pointing out of the board, an electric field pointing down, what direction are your electrons and protons going to move? Now, again, you're going to use your right-hand rule, where, as a reminder, you, in a cross-product situation, you point your fingers in the direction of the first term, so that's E in this case, and then you curl your fingers in the direction of the second term, which is the magnetic field in this case. So you're going to, I'll walk you through this one. You're pointing your fingers in the electric field direction, and then you're curling it out of the board in the direction of the magnetic field. And now your thumb is pointing in the direction of the drift motion. And that will be for the electron, or actually, sorry, I messed that up. That's for both particles, actually, because it's just a cross product. So if you were pointing your thumb to the left, then you were doing it correctly. Okay, so now we have another part of the equation, which is we call grad B drift. And this is because particles actually feel a force and will move when there's a gradient in the magnetic field. A gradient means you have at one place a stronger magnetic field and another place a weaker magnetic field. And a gradient points towards the stronger field or the larger number. So in our drawing here, we have an arrow pointing towards the stronger magnetic field. That's the direction of the gradient. We have our magnetic field pointing out of the board. And then here is our equation. So I'd like you to just take a second on your own to try that right-hand rule with this equation and pay attention to all of the terms. This is actually kind of a tricky one. And this, actually, I'll stop talking for a moment just so you all have a chance to try using your right-hand rule to see what direction will the ions go and what direction will the electrons go. Okay, hopefully you've had a chance. So here's the answer. And the reason that the electrons are drifting one way and the ions are drifting the opposite way is because there's a charge term here in the drift equation, which means electrons have a negative Q and ions have a positive Q. So that will change the direction that the particles are moving. There's also this negative term here. So if you those little sneaky, after you do the cross product, you have to switch the direction. But then for electrons, you switch again because you have a negative Q. And for conceptually, why would a gradient in the magnetic field change the direction the particle is going? It's because the gyro radius, so the radius of this gyrating particle is defined by its energy and the magnetic field strength. So if the magnetic field is stronger up here, you can see, because B is in the denominator, that the gyro radius will be smaller. But where the magnetic field is weaker and smaller, the gyro radius will be larger. So this particle's gyro radius is just changing as it gyrates. And because it's smaller up here and larger down here, it ends up drifting. And a faster particle will drift faster, or more energetic particle will drift faster. All right, so I wanted to do some more activities with you guys just to make sure these concepts are kind of going through. So I'm not going to test you, but if you have like a piece of paper, you could try drawing it out or just conceptualizing in your mind. We're going to try walking through how particles move in the magnetosphere. So in our first case, we're going to just draw convection electric fields. So if you have the magnetic field, or sorry, the Earth's plasma pause here. So here's our magnetosphere. The sun is to our left. We're looking down on the XY plane. If you recall from our previous discussion on convection, we had an electric field that is pointing. We have somebody off of mute. Maybe we want to make sure we're on mute. So our electric field is pointing to the west or across the Y direction. So now let's just, for the sake of this exercise, assume that BZ is constant everywhere, and you have this constant electric field going across the magnetosphere. And we launch particles at different locations across the tail. Well, how are these particles going to move? So we use E cross B. Take a second to think how these particles are going to move. If we just have a constant electric field pointing in the Y direction and a constant BZ pointing up out of the screen. Okay, if you drew arrows pointing towards the sun, then you are correct. So you have, this is just part of our background convection, particles and plasma moving towards the sun. And that's all related to this dawn-dusk electric field and BZ pointing out of the screen. Another way to think of it, actually, one of my professors said, is it's the particle motion creating the electric field. So really, it's these particles that are convecting towards Earth that are creating this electric field in the dawn-dusk direction, because you have particle motion in a background magnetic field. But when we do simulations, which Slava will be talking about in the next lecture, we often define the fields and use that to define the particle motion. All right, so there's another electric field in the system besides the dawn-dusk electric field, and that's the co-rotation electric field. And so I'm going to go through this a little faster than I otherwise might, but how do we calculate the co-rotation electric field? Again, we have E equals negative V cross B, and we have a rotating Earth, and so that's creating our V. And V is calculated as the angular velocity times across the R being the vector pointing out from Earth, which is 2 pi over 24 hours, since Earth rotates in 24 hours, times the distance away from Earth, that's R. So how would the co-rotation electric field profile look on the equatorial plane? We're going to draw co-rotation electric fields now, and I'll do this for us. So the co-rotation electric field are going to be vectors pointing towards Earth. And that again is because now we have a velocity that's going in a counterclockwise direction. So that's our V here. And then we have BZ coming out of the plane of the screen. So that's going to create a vector for the electric field pointing towards Earth everywhere. So now we're going to launch particles from several points. How would the electrons move and how would the ions move in a co-rotation electric field? I kind of already answered this question for you. So I'll just go forward and yep, they're moving in that counterclockwise direction. And again, that's more because they're moving and they're creating this electric field. All right, so now we're going to go back to our grad B drift. So what direction is the gradient? We're treating, now instead of BZ constant everywhere, let's treat this as it actually is, which is a dipole at Earth. So at Earth's dipole, we have a stronger magnetic field at Earth, and it becomes weaker as you move away. So what direction is the gradient? As we mentioned in the early part of the lecture, the gradient points in the direction of the stronger magnetic field. So that means the gradient is pointing towards Earth, no matter where you're located. So now we're going to launch energetic particles. How will the electrons move? I'd like you all to take a little second to think about this now yourselves again. Either draw on your piece of paper or think about it if you're good at just conceptualizing in your mind. Using this equation to guide you, if there's a gradient in the magnetic field pointing this way, what way will the electrons move? Okay, if you said in the counterclockwise direction, you're correct. Again, this is just assuming the gradient in BZ is the only force at play right now. And as I was kind of mentioning before, these are energy dependent because of this term here, mv squared over 2. So what that means is that if you have a more energetic electron, it is going to move faster than the less energetic electron. And that becomes important when we study things like particle injections, which I'm going to come to in my second lecture. So kind of just keep that in the back of your mind. So, what about ions, protons? How will they move? Take a second to think about it. Okay, if you said in the counterclockwise, or sorry, in the clockwise direction for ions, you would be correct. And it's the same cases for electrons. If it's a more energetic ion, it is going to move faster than the less energetic ion. So this is the case for ions, and electrons move in opposite directions. There's one more term called curvature drift. And so this is applied for particle, the previous discussion applies for all particles, but it would have ended there if we're just talking about what we call 90-degree pitch angle particles. 90-degree pitch angle particles are just gyrating at the equator. They don't move up and down the field line at all. They just stay right at the plane, at the XY plane. And so these two terms up here would apply to them. But if a particle has an off 90-degree pitch angle particle, meaning it is gyrating along the field line, not perpendicular to it, but it can actually gyrate up and down this field line, then it has another term, and that's called curvature drift. And that is applying the energy of the particle that is in the direction of the field line, so the energy that it's taking going up and down. And then it's a cross product between the radius of curvature of this field line and the field line magnetic field value. And that, let's see. I thought I did not. So basically it's the same concept as the previous one with grad B. So you have electrons, if you go through this whole cross product story, electrons moving in the counterclockwise direction and ions moving in the clockwise direction, with the more energetic ones moving faster. Okay, so this is a little bit harder, but I wanted to try giving you guys this exercise. And so now we're going to apply all of those factors. So assuming we have a dipole magnetic field with a gradient pointing towards Earth, we have a co-rotation electric field that's pointing towards Earth, we have a dawn-dusk electric field that's pointing in the westward direction, and we launch our particles here in the tail. How are these electrons going to move? If you were to draw their entire trajectory, starting here, all the way until the end of their trajectory here at the magnetopause. So I'd like you guys to take a minute or so to think about what that might look like. And again, maybe take out your piece of paper and draw it. If anybody feels like they want to share, they could always turn on their video screen and show. I'll leave that option for you guys if you would like, but I'll give you about a minute to think about that. All right, is anybody brave enough to share what you might have drawn on the video screen? Yes, as Mark has said, feel free to unmute or type or show your answer.
5 million points for anyone who's willing to interact.
All right, that's okay. We have a multiple choice coming up later that maybe people will feel more comfortable talking. This was hard. I admit this was hard. We have one. Would electrons primarily move in a counterclockwise direction? Good answer. So you'll see that yes, after they reach a certain point in their trajectory. So Sarah Henderson, extra points for Gryffindor. Assuming you're a Gryffindor house, sorry. Harry Potter reference. So this is what the entire particle trajectory would look like if you combine all of those factors. And the reason why it's not completely counterclockwise is because far out here in the magnetotail, the grad B component is weaker and the dawn-dusk electric field component is much stronger. So they initially start out with a mostly just heading in the xward direction, heading towards Earth. But as the electrons approach Earth, the gradient in the magnetic field becomes very strong because that dipole magnetic field is just increasing exponentially. And so the gradient and the curvature terms take over, and those electrons, as Sarah mentioned, oh, Ravenclaw, sorry, 10 points for Ravenclaw. As those electrons grad B drift around the Earth in the counterclockwise direction until they exit out the magnetopause. But there's an interesting story here too, whereas as you can see, these guys coming in from the tail could never get super close to Earth because they just grad B right around it. However, if they started closer to Earth, then their motion is just defined by the co-rotation electric field. And so they're just going to orbit around Earth and essentially stay there until some kind of loss mechanism causes them to be lost to the ionosphere usually, or be able to break out of this separatrix. So this is called an alphane layer or a separatrix, and this is an imaginary line that separates these particles that are drifting in from the tail and cannot get into the inner magnetosphere because they're gravity drifting around Earth. And those who are in the inner magnetosphere just stuck co-rotating and also gravity drifting, but they're inside here, so they're basically trapped. Okay, so here's our multiple choice, and it's also a little bit mean of a question, so I'll just say that. But using this equation as a reminder, if that was our electron contours, which plot below represents the ion motion and the ion alphane layer? So take your time, remember all of our terms. Remember that there is an energy component. That's my number one hint here. It's a bit tricky. And your answer could be left, right, or both. So does anyone want to wager a guess in the chat? And your answer could be left, right, or both. All right, we have an answer from Pauline, and she says both, depending on energy. So Pauline, ding, 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 10 points to your house, whichever that is. That is correct. So the reason both are correct is exactly what Pauline said. Oh, also Ravenclaw. All right, 10 points to Ravenclaw again. So we have, there's an energy dependence on how the ions move. And so the left would be for energetic ions, and that's because they are affected by grad-B drift because of this energy component here. And then they move opposite from electrons, so that Q term, that's why it's just completely flipped. However, when the ion has zero energy, you have to get rid of this term. There is no grad-B drift. They don't move. They don't feel the gradient at all. This is just zero. And so when they're coming in here, this is just the co-rotation electric field basically that they're feeling. So that's great job, Pauline. All right, so then the question though is, well, how do particles get past that alphane layer? Because otherwise, are we always only seeing these particles launched out here just escaping and those in here trapped? But if these trapped ones eventually get lost to the ionosphere, how do we replenish the particles in the inner magnetosphere? How do we replenish the radiation belts? So there's two ways. One is, we were talking about that solar wind driving. So a faster solar wind will create a larger dawn-dusk electric field because, again, V equals E cross B. So if you increase E, you increase V. And then vice versa. Now that you have a stronger electric field, stronger velocity, the component of the dawn-dusk electric field is stronger than the component from the gradient in B. And so that squeezes the alphane layer smaller. So particles can get in farther before the grad-B term in their motion takes over, opposed to the dawn-dusk electric field component of their motion. So that's one way that particles could get in. And then once the driving slows down, those particles that made it in are now trapped, stuck there. So that's what we call more like a global injection, large scale, but there's also these localized fast flows, localized particle injections. So here I've drawn those contours of motion again, where now I'm looking at an individual electron, so in blue, and again, before injection, it's just drifting around the Earth. But now if you have a very localized plasma flow in the tail, say after reconnection, you have a sudden burst of flow that is traveling towards Earth. That has a very intense dawn dusk electric field inside of this flow, because again, your V is towards Earth, your B is the same, pointing out of the page, and so your E is pointing downward, or towards the dusk from the dawn. And so that strong electric field means that locally, the dawn-dusk electric field component of that V cross B whole equation is stronger than the gradient in B, and the particle can make it in farther before it starts to feel the effects of the gradients of B and go around Earth. And so here's the picture of that particle after it's been injected in. Now it's trapped. Now that flow disappeared, it made it from outside to in. And so this is just a cute little drawing or figure movie, I guess, showing how you can use those equations, those particle equations of motion, to model how these particles are moving in the magnetosphere, in the magnetotail. And so the top panel you're seeing here, the color bar is the magnetic field. So here's our dipole magnetic field near Earth. It's decreasing out into the tail, so that's why our color goes towards purple. And the bottom two, we're seeing the strength of the electric field plotted. So the color is the electric field. And so what you see moving here is this very narrow, fast flow coming earthward after reconnection in the tail. And then what you do as a modeler, which Slava will be talking about more in his lecture, but I wanted to touch on here since the summer school is about how models inform data, or data inform models, they're all connected. After you, with a model, you define what are your electric and magnetic fields in the system, and then you can launch these particles and have their motion be defined by those equations we just discussed. So here's a 0.1 keV electron, so it's not very energetic. And so what you see, this green one especially, its motion is primarily defined by that strong dawn-dusk electric field inside this narrow flow burst. And it's just carrying that electron deeper into the inner magnetosphere, and it doesn't really feel the effects of grad B. If we go to a more energetic particle, a 10 keV electrons, now their motions are being more affected by the gradients in B. And so you can see this local flow also has BZ component. That's why we see some color up here, because it's bringing in a stronger magnetic field line. And we're going to talk about more of this in my second lecture, why that's happening. But here you're seeing this particle is grad B drifting around that local BZ here, and then it comes in farther before being injected. And then if you go to the most energetic particle, their motion is almost entirely defined by the gradients in B as opposed to the E cross B drift. So especially you can see this light blue particle, it's moving around this flow because of the strong BZ that this flow is carrying in. And that's because its motion is just, primarily defined by grad B. So this was just a nice little cartoon to kind of illustrate how different particles with different energies have very different motions based on the fields and the gradients in those fields involved.
So there's a quick question on, is this just a test particle, or were you throwing in?
Yeah, so great question, again from Sarah. What modeling techniques were implemented here? So yeah, this is very simple. We call this an analytic model. So this is just Fortran code where I literally defined what are the background magnetic field, and then what is this, this flow coming in here. So it's not MHD, it's not something fancy. It's just using literally equations, and you just set this, make the equations a function of time, which is how you get this piece moving in time. And then you just define the particle, how they move with using those equations. Again, it's then a function of time. That is how this moves forward. Hopefully that answered. Yeah, it's not particle and cell. It's very, very, very simple. So this takes us to the end of the first lecture. But as a transition, we'll be moving to also talk about convection on mesoscales. So what we just saw was a mesoscale. So these are embedded in background convection pattern, and mesoscale phenomena actually carry the bulk of the load. So that little flow burst you saw that is only a few RE wide, that is considered mesoscale. And so there are lots of papers. Angelopoulos is one of the first showing that bursty bulk flows, these mesoscale, very fast flows in the tail that are going earthward, transport the majority of the magnetic flux earthward on the night side. And then actually these mesoscale phenomena start at the beginning with day-side reconnection. And just to define, they are in the magnetosphere about 1 to several RE wide. In the ionosphere, they're about, mesoscale means 50 to 500 kilometers wide. And so at that point, we're going to stop for our break. I don't know, Mark, unless people have questions, but that's what I have for the first lecture, and then we'll move on to the next lecture after the break.
Great. If anybody has any questions, feel free to raise your hand or unmute yourself or type in chat. If not, Nick, any directions for coming back at the top of the hour?
I think that's just fine.
Great. So we'll kick off the second part of the lecture at the top of the hour.
Sounds good. See you guys then.
Thanks. So if you can give a thumbs up or turn on your camera, give indication of how many folks are back. Got a couple cameras and a lot of thumbs up. So looks like we're ready when you are, Christine. And I see
Okay.
you answered a question in chat. So great, thanks.
Sure. All right. Welcome back, everybody. So now that we covered some of the fundamental theories and ideas of how convection works in the magnetosphere, the second half of the lecture is now to look at the actual data. So I'll be introducing you to some different data sets by actually going over some papers that have studied these mesoscale convection features in the magnetosphere. So starting from day-side reconnection, where it all begins. When you have day-side reconnection, this magnetic field line from the sun, as we discussed, connects to the Earth's magnetic field line, and then this IMF drags the magnetic field line from Earth backward into the tail. Now, that looks like this flux tube here, which was sketched in 3D from a paper from Russell and Elphick in 1979. But then as this is being dragged backward in time, or backward in space, over time, As we mentioned in the beginning, you have these flow patterns going across the polar cap. And because this is localized in what we're calling mesoscale, it's not the entire front of the day side going off in reconnection at once. It's localized to just a portion of the magnetic field. We have very localized fast flows going across the polar cap. And as I mentioned in the beginning of the last lecture, one way to measure those flows is using radar, which are based on the ground. And so you'll see, actually, to study the magnetosphere, we don't only use data from satellites, we actually use several different kinds of data sets that are based on the ground. And what's great about this is that they give us a two-dimensional picture of what's going on. So here's an example of what Super Darn showed us, which, us meaning a community, this isn't my paper, it's by Milan et al. But it's a localized fast flow here embedded within, very slow background convection patterns. And that came after day-side reconnection. And this fast flow was observed by Super Darn, but it was combined with another data set, this image, FUV-WIC. So this was a satellite that was up in space looking down and capturing what the aurora looked like in the ultraviolet wavelengths. And so here is the aurora, this red color here in this oval shape. And you can see this mesoscale auroral feature, this bump right here, which is related to this fast flow. And that's called a PMAF, which stands for poleward moving auroral form. And that's because after you have day-side reconnection, as those field lines are moving across the polar cap, they're initially moving towards the pole when you're still on the day side. So this auroral form is moving towards the pole from the day side towards the night side, and it's related to this fast flow. So these are two different types of data sets observing the same phenomenon. And here this is a nice study if you want to see this entire process when it starts on the day side with this PMAF, this poleward moving auroral form, and then moving across the polar cap until it reaches the night side, where then you have reconnection and what we call auroral streamers. So these are mesoscale streamers in the aurora, and those are related to those fast flows that we were talking about in the last lecture in the magnetotail. So I wanted to show this study because this is another ground-based data set that is observing how these mesoscale flows move, starting from the day side, moving to the night side. And I wanted to spend some time explaining how to interpret this figure because I figured maybe a lot of you are not familiar with kilogram. So kilograms are plots that plot the latitude, in this case magnetic latitude, on the y-axis. Whereas you probably know latitude lines run east-west and they measure how far north or south something is. And then the x-axis is time. So what you're looking at with a kilogram is just like a one longitudinal cut across your two-dimensional picture. So this green line is just an illustration of what the y-axis represents in a kilogram. So here we're looking at the red aurora on the day side, where latitude starts more towards the equator, moving towards the pole as we increase the y-axis. And so if you see a feature like here that starts at a low latitude and moves to a high latitude over time, that means you're observing something that is moving poleward over time. So that's how you interpret a kilogram. So this kilogram is observing a poleward moving air glow patch. So that's after reconnection, they see this poleward moving patch of the aurora. And then this is just a different wavelength. This is green aurora, so they see the day side brightening. This is that polar moving auroral form. And then here again is our radar data. And you can plot radar data in this kilogram form as well by making the color show what is the velocity. So in this plot, black means it's a negative direction, red means positive direction, where black means anti-sunward, so something moving towards the night side, and red would mean moving towards the day side. So here they're using super darn to show that there is flows in the polar cap that are moving towards the night side of Earth. So that's basically this thing moving from the day side to the night side. And now we're here in the polar cap, in the polar cap, but on the night side. So here where you can see then how this aurora is starting at a high latitude and then over time moving to lower latitudes. And so that means now that we're on the night side, that it's something moving anti-sunward towards the equator on the night side. And then this is super darn data again, where now the red positive is meaning anti-sunward. So this thing is moving away from, again, away from the sun, still continuing tailward over time. And then aurora again, where they're showing just how the aurora is brightening along the top of the aurora oval in what's called polar boundary intensification. So the main point of this slide was just to introduce you to this type of data and how to interpret what we call a kilogram and how it observes these modes of convection that we've been discussing. So I thought I had moved this movie earlier in my talk, but this movie is just to show you what a substorm looks like, where we have day-side reconnection from that southward pointing IMF, dragging those field lines back into the tail, stretching that tail until the magnetic field lines in the tail reconnect as well here. And then they shoot back towards Earth in what we call dipolarization, because the stretched magnetic field line is becoming more dipolar in shape. And as it does that, it transports particles towards Earth. Those particles precipitate into the ionosphere and create the beautiful aurora. And also field lines are cycling back to the day side. So we'll watch that one more time, if it will let me play it again. And this is just a movie to illustrate that the substorm and convection patterns that we've been discussing. I always find it so much easier to visualize things when people make nice movies like this in 3 dimensions or even 2 dimensions. So now we've got a tail connection here, that fast flow heading towards Earth and particles being dumped into the ionosphere. And the duration of a substorm is an average 90 minutes and can happen about once a day. So here's just another illustration of the substorm. This is from Hohn's 1977 paper, also pretty famous. And there's 3 timing sequences proposed that the Themis mission was launched to help answer. And that kind of landed on number 1, although number 3 is kind of related and is having a lot stronger support nowadays. So the first being near Earth neutral line, which is you get that tail stretching. And I should mention, because I didn't already, you do always have this distant tail X line. So you always have this distant tail reconnection occurring quite far out in the tail, like on the order of 100 RE or something. But what we're talking about when we have these substorms are what we call near Earth reconnection. And so that happens here closer to 20 to 30 RE. And so when you have that near Earth reconnection occurring, you end up shooting a plasmoid down the tail, because when they connect, all these field lines back here have to go somewhere. So that heads off down the tail, and then you have earthward motion heading towards the earth. And then again, you slowly just build up that stretched tail again. So the current disruption timing sequence views it that when you have the tail stretching, you end up stretching it so thin that the current sheet can't handle it. So an instability forms around 9 to 12 RE. And that current is then diverted along magnetic field lines into the ionosphere, creating the substorm current wedge, terms that we'll discuss in a few slides. And then the dipolarization forms, and that can trigger a reconnection and earthward flows. So just the order changes. This streamer-triggered substorm is something that was suggested after the Themis mission, which is you get, say, that distant X-line formation, and a flow comes in from that distant X-line, reaches a stretched, thin, unstable current sheet, and triggers that instability, which results in the substorm. So with the first option, it's like you have the near-Earth neutral line form, which then creates dipolarization and substorm current wedge instabilities. For the second one, the instability forms first and then leads to reconnection and fast flows. For the third one, you have the stretching happening, but the instability doesn't go off until a flow comes in from the X line and triggers something, the instability, and then the whole substorm. So to look at the data related to a substorm, I wanted to, again, teach you guys how to interpret these squiggly line plots that you see from satellites in space. And this cartoon is to help us visualize what the magnetic field looks like. So remember that BZ is pointing up, and that is going to be the red color in our magnetic field line plots, and BX points towards the sun, and that is going to be the blue color. And so when you have a stretched magnetic field line, like before reconnection happens, most of that component is in the X direction, as you can see here. The magnetic field line is pointing almost totally towards Earth or towards the sun. And if you're north of the neutral sheet, it'll be a positive BX because it's pointing towards the sun. If you're below the neutral sheet, it's a negative BX component because it's pointing away from the sun. So when you have a reconnection and what we call dipolarization, this stretched field line snaps back towards Earth and forms a more dipolar shaped magnetic field. And so now you see the component of the magnetic field at the equator is almost entirely in the BZ direction. And so we can look at that in the actual data. So this second panel here is our magnetic field plotted, where again, red is the Z component, blue is the X component, green is the Y. This dashed line represents 0. So here you can see the tail stretching happening because BX component is increasing in magnitude. You can see this, it goes down, it starts around -10 and increases to -30. And since it's negative, we just know that we're below the neutral sheet. We're down here as this is stretching and the BX component is increasing and BZ is decreasing. Then we have our reconnection or our substorm onset, and we have dipolarization. So as that field line snaps back, you see BX component seen by our satellite suddenly decreases in magnitude, and the Z component increases in magnitude. And that's because it's going into this dipolar shape. Now, along with that dipolarization, we usually see what we call bursty bulk flows. These are really fast plasma flows. So again, blue color means that the flow is traveling towards Earth. And so you see these strong blue spikes in the velocity data here occurring with the dipolarization. And again, that's just because these are slingshotting back towards Earth after reconnection. But you do get some Y component sometimes, that's the green, but very little Z component here because we're near the equator. So along with these flows, oh yes, we have the top panel is our AE index. It's a magnetic indice, so it kind of gives us a feel for how strong the substorm is. So that's why we see this spike here. But along with those, going back to our satellite data, along with those fast flows, we get enhanced electric fields. And again, green is the Y component, and that is what we see spiking here. And again, that's related to our equations at the first lecture. When you have a strong V in a strong B, you get a strong E in the perpendicular direction. So again, V cross B, you get E in the Y direction. And at the same time, you often get these density depletions because as these are coming in, these were originally very stretched field lines, so you have less dense particle populations here. And then finally, you see particle injections. And so these plots here, what we call spectrograms, they're plotting the particle energy on the y-axis. These are for electrons. And time is on the x-axis. And the reason there's two panels here is these are two instruments on the same satellite, but this instrument looks at the less energetic particles and this instrument looks at the more energetic particles. So we just plot them on top of each other to get like an overall feel for the particle energy flux. So the color that you see is particle energy flux, and that gives you a feel for basically how energetic, how much energy these injections are bringing in. So obviously the y-axis is the actual particle energy. So this is, you can see it as like how many particles are coming in, like the flux. And let's see, yep. So you've got this very strong particle injection at the same time as dipolarization. And I will later show you another way to plot particle injections with line plots. We'll get there in a minute. So you can use data because satellites are just one point in space. In order to tell a story, you often have to use statistics. And so you can use years of satellite data to try and understand the overall convection pattern, which is what this study did. So they used years of satellite data to look at how fast are these flows that you see coming in at different distances from Earth. And so they found that the flows after reconnection accelerate. So here the x-axis is the distance from Earth, and the y-axis is the velocity strength, Vx. So what this shows us is that the flows, when they're coming towards Earth, are actually accelerating until about 15 RE, and then they start to decelerate. They're slowing down. And so that's what statistics can be used to do. And this study was explaining the forces involved. So you can read this paper by Lee et al. If you're really interested in how the forces explain how this happens. But the overall idea is that you have a curvature force, which is very strong when you have a stretched field. It's kind of like a rubber band that you're pulling back that has all this pent up energy, that potential energy that you need to release into kinetic energy. And so this curvature force is very strong. And so when reconnection happens, it slings this magnetic field line back towards Earth. But dipole magnetic field, there's also magnetic pressure, which is pushing in the opposite direction. So at some point, that curvature force is going to equal the pressure force from the strong dipole field, and that's going to slow it down so that, these field lines don't crash into Earth's surface. They eventually stop at an equilibrium point. And that's why they are decelerating. Another way to think of this, which is hard to look at with data, but easier to look at with models, is to think of it in terms of a bubble. So a magnetic flux tube, so you think about magnetic field lines form these, what we call flux tubes. They each have a certain amount of entropy, which is defined as PV to the gamma, or pressure times volume to the 5/3. And so if just before reconnection, ignore this little bubble here, you would just, entropy increases the farther you are from Earth. And you could simply think about it as the fact that the volume of a flux tube is larger farther from Earth, because you see the magnetic field line is so much larger, so much longer. So the volume is larger, so the entropy increases. But if you suddenly have reconnection, sorry, my computer needed to be plugged in. All right, but if you have sudden reconnection, that flux tube volume is just suddenly decreased, like a sharp decrease here. And so that's what this little drawing shows, is a bubble, what we call a bubble after reconnection, because that flux tube's volume just suddenly decreased out of nowhere. And so just like an air bubble needs to rise to the surface of the water, an entropy bubble needs to rise to the surface of the entropy, or basically find the point in the distance from Earth where entropy is the same. So that's another way to describe how these flux tubes move earthward until their entropy equals the same as those flux tubes closer to Earth. And so again, if you want more details on that, you can read papers about it, the Sergeyev paper. There's lots of Wolf papers about it. All the references are listed here. But how do we observe this in using satellite data? Well, it's very hard. It's almost impossible to measure entropy, as I mentioned, but you can measure the effects of the earthward traveling dipolarization. And that's what we see here. So in this figure by Aronoff et al. Paper, the Themis satellites were situated at different distances down tail. So this is the x-axis, and this is here's Earth and our magnetic field lines. And after reconnection happens, there's this dipolarization that moves earthward. So they observed it first at this red satellite, this P1, then at the next satellite, P2, then later at the 3 inner satellites, P3, 4, and 5. So Themis was designed to actually observe these dipolarizations as they travel earthward. And so, as we mentioned earlier, more than 60% of the magnetic flux in convection is carried by BBFs. So that means, if you remember, we talked about global convection, where there was that overall motion of the plasma in that Dungy cycle. But then we have these mesoscale bursty convection, these flows after reconnection. And so most of the total magnetic flux occurs in these bursty mesoscale flows. And that's what this study used satellite data to look at, where here we have the flow bursts, again in blue, for they're traveling earthward. And embedded in those flow bursts, down here we see the magnetic field is plotted. We see these spikes in VZ. So these are these dipolarization fronts as these flux tubes are moving past the satellite over time. And they actually calculated how much flux, magnetic flux, is being transported over time in this last panel, showing with each bursty bulk flow, these bursts of velocity, you see a spike in the flux being transported earthward. This paper is another example of using statistics. So they used, data from years of satellite data and calculated the magnetic flux over during substorm growth phase, substorm expansion phase, substorm recovery phase, just to show where was the magnetic flux happening. So you see a lot of magnetic flux transport occurring here during the substorm expansion phase. And that's when reconnection is just going off, boom, 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 boom. So it makes the most sense anyways. So substorm dipolarization. So this, after you have the dipolarization occurring from reconnection, because it's happening so fast, it actually can start to pile up magnetic flux near Earth because it's transporting that magnetic flux faster than it can be dissipated around to the day side. So here's just a cartoon picture of that, where you can see dipolarizing flux bundles coming in, and they're building up this pile-up region of magnetic flux into a large-scale dipolarization near Earth. And Slava will, I'm sure, be showing you this movie or similar ones in his talk. But again, just to connect the data with the models, here we can see the red is earthward in his model. So you see earthward flows coming in. And as these earthward flows are coming in like narrow fingers towards the Earth, it's building up here BZ, which is the red color, increase BZ in this region here, this pileup of magnetic field. And here he showed an increase in pressure, and that's because it's just piling up that BZ, that magnetic field component here. So that's the nice thing about looking at data and models together, is that often as we show, the data just shows us line plots, or we have to use statistics to get an overall picture, whereas the models can give us this 2D or even 3D picture that we can then interpret, or use our data to interpret, or use our data to validate in some cases. There we go. So this is just an example of more data sets. So as these flows are coming in, they will eventually be diverted as they can't penetrate any deeper. And this diversion can cause Kelvin-Helmholtz waves, which are observed in the ionosphere as omega band aurora. So here's just a sketch of the shape of an omega band aurora. It's given the name omega because it looks like the Greek letter omega. And the authors were saying we can observe the fast flows that are being diverted from this this whole series of phenomena by using satellite data. I believe they use SWARM, so that's a low altitude satellite that's observing features in the upper ionosphere. And so this blue, or I should start with this yellow line, is just drawing the border of the omega band aurora. And here they show the velocity in the ionosphere, which is kind of steady and then suddenly increases a lot on the poleward side of this omega band aurora, and then goes back to normal. And so this is just an example of using satellite data to observe the flows that happen to be in the ionosphere, but again, because the ionosphere and magnetosphere are connected, these flows are also happening in the magnetosphere. So I mentioned a substorm current wedge. This is essentially what happens during a substorm when you have dipolarization, because you have current going across the magnetotail. Without the substorm going on, it just goes from the dawn-dusk direction, the same as the electric field. But then when you have, so here, this dashed blue line is meant to show a contour of the dipole magnetic field. So when you have a dipolarization, that contour goes out into the tail and then back in, because here's our pileup of magnetic field. So that current hits that and can't continue. It needs to go somewhere. So it travels along the magnetic field lines into the ionosphere. It crosses across the ionosphere in the west direction, and then exits again out along the magnetic field lines and back into the tail. And so this substorm current wedge is something that we can observe both on the ground and with satellites. And so this is an exercise I wanted to do to practice looking at data, again, from the ground, which helps us to understand what's going on in space. So we're looking at this substorm current wedge, which I just showed in the last slide. And as this current needs somewhere to go, as I mentioned, it comes in the westward direction across the ionosphere. So if I take a 2D cut of that current, so now in this 2D cut, the current is coming out of the page. So that means it means we are west. In the west, we are looking in the east direction, and we are to the west. So to the right on the x-axis is the equator, and to the left on the x-axis is the North Pole. So using Ampere's law, we use our right-hand rule to point our thumb in the direction the current is traveling, which is out of the page, and our fingers curl, and that shows us the direction of the magnetic field that is created thanks to this current. So this magnetic field, here we see in the counterclockwise direction, you can measure on the ground using magnetometers. So this is an instrument that, again, we use on the surface of Earth to measure these perturbations in the magnetic field. So this magnetometer will always measure the Earth dipole field, but then it's going to, when this current occurs in the ionosphere, it's going to measure perturbations in that background field thanks to the magnetic field created by this current. So the coordinate axis used with magnetometers is Z points towards the center of Earth, H points towards the north, and Y completes the perpendicular direction to those two. So you can see that if you are north in the northern hemisphere, poleward, basically if you're poleward of the current, you're going to see a strong Z component in this perturbation magnetic field. If you're south of the current, you're going to see a negative BZ component. And then if you are directly below the current, you won't see a Z component, but you'll see a strong negative H component. And if you're somewhere in between, you'll see a bit of Z and a bit of H. So these figures here show you the data of multiple magnetometers. We call it a magnetometer chain. So these are plotted from north to south, where here are the different station locations. So NAL, NAL, Longyearbyen, Longyearbyen. You can see where they're located according to this map. And the red lines here are just pointing out when that perturbation begins. So you can see these perturbations where this left-hand figure is the H component. So that's pointing poleward. And the right-hand figure is the Z component. So that's pointing towards the center of the Earth. And so this was another exercise I wanted you guys to do to practice interpreting data. So using all of these magnetometer chain data, you could actually determine where this current has formed in the ionosphere. So I would like you guys to think about where, what station, between which two stations did this current form? And how did it evolve? Just looking at this data. So I would like you to answer in the chat, or you can go off mute if you're super brave and tell us what you think. So let's give everybody some time. Again, the question is, where did this current form based on this magnetometer data? And the answer, you could say like at this station or between these 2 stations.
Christine, could they annotate the map?
Can they?
They can. They use the annotate tool to put a stamp on slides. So.
Oh, that's awesome. I didn't know Zoom had that feature. Maybe not being a professor, I'm not as up to date. So yeah, feel free to annotate the slide. Thanks for the suggestion, Nick.
A warning, when you erase it, it might take a while for you to get your cursor back. We've been discovering that bug.
Oh, okay. All right, we had the first input from Sanjay. Anyone else want to annotate? Oh, we have an answer in the chat. We have Hor and Hop. I'm sorry, I don't know the names of these stations, so I'm not Hor or Hop or BGN, depending on the peak. A high peak, I mean. I'm just reading an answer from Hasna in the chat. Oh, we have a few more annotations. All kind of converging around similar locations. Give you just a few more seconds if you want to throw in your, I don't want to say guess, I should say your answer. You have one put in at the pole side. All right, so I think everyone has had a pretty adequate time. So great job. Most of you did an excellent choice. The answer is it started just south of HOP and then moved over it, which you can tell here. So you're all, I think these are all correct. You see this positive term, BZ term, which means that it started just wait, where did I draw that wrong? Positive BZ means, let's do this on the fly, means that it should be poleward, and then it moved to negative BZ, so that it moved, oh, that's why, yeah. So it was located north of HOP, and then it sees a negative component, so it moved, sorry, HOP was north of the current. That's why I just confused myself. I do it right correctly. So the station was north of the current initially, and then the current moved poleward over the station, so we get this negative component. and then it evened out. And you see the strongest BH component, which meant that HOP was right underneath the current at this time. So everyone who drew it around here is correct. Good job. Give 10 points to your house. Oh, I see what you meant about erasing these annotations.
Yeah, if you go to your annotate button, that's maybe either under view options at the top, or you might have it on your bottom.
I see it. So I click eraser.
You click eraser, yeah.
I got it already.
Oh, awesome.
Thank
Thanks,
you.
Nick.
Nick is honest.
Our co-host.
Okay. All right, awesome. So great job, everybody. That was looking at the substorm from the ground with magnetometers. But I would be remiss if I didn't talk about one of the giants in the field who first observed substorms from the ground with just his eyes. So in this case, his eyes were the instrument. This is Akasofu, and he would sit outside in Alaska and just watch substorms, and was able to see by watching so many of them that they followed a similar pattern in the aurora, and he sketched that pattern. And so one of our first substorm papers from 1964 is hand sketches of the aurora, which showed how you had these quiet arcs that then moved equatorward and intensified until you had this explosion of aurora that then traveled westward and poleward, and had a lot of these. Here he drew those omega bands you can see here on the east side and everything. So because many of us maybe have not seen the aurora, I wanted to include this video. So this is using All Sky Imagers, which is another ground-based data set that observes the aurora, which again is just a way to visualize what's happening in the magnetosphere in 2 dimensions. So here we have that, sorry, I sped it up so it would happen very fast, but you initially see just this quiet arc at the bottom, which then explodes. We'll watch it again. Here's that arc, and now it explodes into this westward traveling surge as it travels west here, and also increases in the polar direction. So that's what Akasofu was watching out in the cold in order to draw these pictures. And now, thankfully, we have these all sky imagers so that in sunny Southern California, I can watch these same events as Akasofu did out in the cold in Alaska, just by bringing up these videos from the all sky imagers. And this is something that I probably should have actually shown you guys earlier in the lecture. But this is just showing how the aurora is connected to what we see in the magnetotail. So because the magnetotail magnetic field lines are attached to the ionosphere, as stuff happens out here, that information maps down to the ionosphere. So as you have these mesoscale flows traveling earthward after reconnection, that creates field-aligned currents along these magnetic field lines that you can observe on the ground. And these field-aligned currents accelerate the electrons along the field lines and create these bright auroral streamers. And because of how the magnetic field is, as a flow is traveling earthward, that maps to something moving equatorward. So that means when you see when a satellite would observe an earthward traveling flow, in the aurora, we would see an equatorward moving auroral streamer. And to come back to our radar data set that we talked about in the first lecture, you can observe that plasma flow that is occurring along with simultaneously to that auroral streamer. So here's a cartoon that is showing you the field-aligned current is created because of these flow vortices created by the earthward flow. As it's moving earthward, you have these vortices that form on the sides, and those vortical nature creates these field-aligned currents. And so Also, because of the plasma flow itself, it's creating the plasma flow in the ionosphere, which I just mentioned will be flowing in the equatorward direction when you have an earthward flow. So you can measure that equatorward flow with the super darn radar, which we've plotted here. So the red color means that there is equatorward flow, and the blue color means there is poleward flow. So these super darn radar data is showing us the flow vortex, where we have the equatorward flow, which again means earthward flow in the tail, and then this poleward flow, which is this tailward flow on the side due to this flow vortex. And right in between the two is where we get this bright auroral streamer, and that's because it's at that, what would you call it, that connection, but where the opposing flows meet is where you have the field-aligned current. And so that's where we get this bright auroral streamer that then travels earthward. And so it's really cool how we can use, again, ground-based signatures to get a two-dimensional view of what's happening in outer space. And if you want to read more about this, here's a bunch of references you can check out. Another data set that allows us to look at information in 2 dimensions are these imagers. So this is from TWINS, this satellite mission called TWINS, and they look at ENA images, which is energetic neutral atoms. And this particular group, this team, has a technique to map the temperatures of the ions in 2 dimensions down space, in space. So this is plotting the x direction on the x-axis, y on the y-axis, and you can see these narrow temperature enhancements, and those are from these fast flows, which are energizing the particles. And then they plot MMS data, so that's the satellite data that observed this happening here. So the MMS data saw the actual flow, earthward flow here, and the particle energization. And what's cool is that they get this 2-dimensional view that they could then have the context of what the satellite is seeing. So this is coming kind of back to some of specifically what we were talking about in the first lecture, and this is particle transport, particle injections. And particle injections were historically studied at geosynchronous orbit, which is at about 6.6 RE. So right when we're transitioning into the inner magnetosphere from the outer magnetosphere. So in order to get new populations here, as we talked about in the first lecture, we need some sort of particle injection to carry those particles deeper towards Earth, because without it, they're just going to drift around Earth and never reach the satellite at geosynchronous. And so earlier in the lecture, I showed you particle injections in a spectrogram form where it looked like very rainbow, very colored. This is a line spectrograph. So these panels are for 3 different satellites, and each line is an energy channel that the satellite is observing. I don't know what they are off the top of my head, but for instance, this red could be, say, 50 keV particle, whereas the orange might be, it's more energetic, so it could be 100 keV particle. And then the y-axis is showing the particle flux, so the number of particles per unit area, per second, per steradian, per energy. And so here is a kind of cartoon picture of this large-scale injection where you have the heated particles behind this front, and it's being transported earthward. And so if your satellite is within this injection region, it's seeing the energization process happening, it's seeing the transport as it's happening. And so what that signature would look like at your satellite is what we call a dispersion-less injection. And that means that every single particle energy channel sees this increase in particle flux at the same time, because you're just seeing this all these particles coming in. But what's cool with injections is if your satellite say your satellite is off here to the side and it didn't see the injection happening when it happened, it can still see the effects of the injection thanks to grad B drift, which we spent a lot of time talking about, right? So after the particles are injected, then they start to feel those effects of the gradient in the magnetic field. So the electrons are going to start grad B drifting in the counterclockwise direction towards the satellite here. The ions are going to be drifting in the opposite direction because remember, there's that Q term. So, and remember also there's this energy term in the equation. So the more energetic electrons are going to get to the satellite first before the less energetic particles because they're moving more slowly. So what we see in the signature of the data is our more energetic electrons down here see the increase in flux before the channels observing the less energetic particles. And so this is what we call a dispersed electron injection signature. And what's kind of neat about the dispersed injection is that you can use the difference in time that the different energies arrived at the satellite to kind of back out where was the actual injection region by determining at what point in space would all of these particles have originated at the same time. So that's a kind of cool way to remotely sense where this particle injection is occurring using satellites off to the side. And this is just another, similar to the other little cartoon movie I showed you, just some work I had done showing that if you have multiple dipolarization fronts coming in with that fast flow, you end up having very sharp gradients in the magnetic field traveling earthward. So even these energetic electrons, which would normally just grad B drift out of the flow thanks to the background magnetic field and therefore background grad B drift, they actually get trapped grad B drifting around these local islands of BZ and traveling farther earthward due to that grad B drift component. I see we're running out of time, so I won't spend much more time on this. I think Slava might spend more time in his talk, but it's very interesting and cool, again, to see how models and data can come together to study these phenomena like injections. And again, maybe I won't spend too much time because I believe I don't want to take Slava's thunder, but kind of as transitioning to his lectures, there are more, what's the nice way of putting it? Well, more physics. Sorry, I'm just blanking. Sometimes I blank on English language, even though I'm an English speaker. Basically, the MHD models in this case are showing the same kinds of effects as that simple model, showing how these islands of strong BZ from the dipolarization are carrying in these energetic particles because they're trapped grad B drifting around these magnetic field islands, being brought into the inner magnetosphere. And again, these are, using those particle equations of motion that we touched on in the first lecture. So there, you can see how important they are in both, well, particularly modeling, but also in data to understand what's going on. So just in summary and to conclude, this lecture focused a bit more when IMF is negative BZ, and you get the substorms and the enhanced convection. But there are, of course, cases when IMF is positive BZ or there's a strong BY component. And so there's a lot of interesting questions when that occurs as well. And I hope one takeaway from this lecture that you have is that mesoscale convection is important, especially when discussing substorms. So not just the global convection, but these narrow flows. And then one thing a lot of people are working on now is quantifying the mesoscale phenomena contribution. And so if you want to read a lot of recent papers on this topic, you can check out this bit.ly/dipfg. We have a NSF Geospace Environmental Modeling Focus Group that tries to collect papers that have been discussed there. People are trying to quantify the contributions to the radiation belts and the ring current, something I didn't have time to go into in this lecture. And then there are vast implications on the ionosphere, thermosphere, mesosphere, because I hope you also take away that the magnetosphere is a coupled system with these other regions of geospace. So global models, which you'll be hearing about next, are working on combining these regions and studying this. So we need more data inputs in order to inform the models how to run. And just as some background, in the US, NASA is taking white papers for its decadal survey. And so that means we as scientists have a chance to inform NASA what we think is important to study scientifically. And so we've been writing white papers to point out we need missions that can capture more of this two-dimensional space to really study these mesoscales and utilize the imaging and 2D data sets that again help us see these mesoscales, not just the global scales. And so coordinating the modeling with the data is also very important, which is kind of cool that that was a theme of this Heliophysics Summer School. So I'll wrap up there, and if there are any further questions, I don't see any in the chat, but if there are any more, I'd be welcome to take them.
Great, thank you very much, Christine. And for the students on Thursday, and our capstone discussion, part of that will be talking about the decadal survey and having you think about where you want to be working over the next 10 years. So
That's great.
Feel free to raise your hand or unmute yourself or type in chat about any of all of the varied observations that are associated with this thing we call a substorm. Yeah, I was an undergraduate research assistant for Shinakasofu, and one summer was essentially looking at film from all sky cameras, and each frame saying moon, aurora, clouds. And then helping him make AE. And so I digitized Russian magnetogram traces that some poor undergrad in Russia had used rice paper to trace over.
Wow.
Pen and paper magnetograms.
Wow. That's cool, Mark.
Yeah, I feel like I'm becoming Bob McFerrin.
Yeah, I have to say, it sounds like you've reached that stud. You're talking about tracing rice paper and
yeah.
Wow.
Yeah, one of the reasons why there's been so much debate and so much study on substorms, as Christine showed, there's so much going on, and everything from the micro scale, trying to understand instabilities, to the mesoscale, that if you're just off by a few RE or even fraction of an RE or a fraction of an hour in local time, you can see very different things. And so this is just sort of screaming for much higher density observations, so we can start seeing, should we trust these MHDs and the Slava Merkins of the world? Or does they just have this crazy stuff going on, as that one of the last slides showed? Great. We actually have office hours now, but we're going to move into those And for those that, this is also the extended break, and depending on your time zone, whatever meal is appropriate. But we'll be coming back. Let me, we have a half hour. Is that the?
Yes.
Yeah, so at the bottom of the hour, and for those in the half hour time zones at the top of the hour. But if you have questions for Christine, if you're able to stay on for a few more minutes, we can see if there's any questions.
So there's a
Sure.
question in the chat.
Great. Do you see from Raphael, what is the difference between region 1 and region 2 field line current?
I feel like I should, as lame as this sounds, I feel like I should Google to show, 'cause I don't have the
Google is your
Yes.
friend.
yeah.
Yep.
You know, the trick is knowing how to use it.
Yeah. Oh, oops, I don't have, that's right, because I'm not.
That's very strange. How can you not have internet connection?
Well, the long story is, I'm using my work computer, and I usually, if I'm on the network, I have to use a proxy. If I'm off the network, I have to not use a proxy, and I can't be on Zoom when I'm on the network. So I'm off the network. So I have to use Firefox to turn off the proxy, and I just tried using Chrome, which requires a proxy.
So the students have seen a couple of slides that showed sort of cutaways of the magnetosphere, and Carol Shriver showed.
There you go.
Yeah, so any of those will work.
Okay, so they have seen this.
Well, they saw the more global one that had ring currents and Chapman Ferrara currents and everything, but also field line currents. But go ahead. Yeah, this is a.
Is this maybe a good one?
Sure. Yep, it's labeled and everything.
Yeah, so the region 2 currents you can see are coming in here. They're more equatorward here on this side. And then they're coming in along the field lines. And then when they reach the ionosphere, they cross up, and then they go out along these magnetic field lines. And you can see where that happens is at the point where convection is basically converting between, in the middle here across the polar cap, you have convection happening from the day side to the night side. And so you have these region 1 currents essentially coming down and across the polar cap and up, where the entrance and exit points are here at, you can see here, this is the, as I was mentioning, sorry, I'm not saying this very clearly, the convection pattern. And right at that shear location where convection is between being towards the night side on one side and towards the day side on the other side, that shear is where the field line current occurs on both sides. So that's your region 1. And then your region 2, you need something coming in and kind of closing that. So these region 2 are coming here on the outside of the convection here, and then closing across the ionosphere and coming back up alongside here. Did that kind of mesh with what Carl Shriver was saying
Yep.
in the earlier lecture?
Yep, and so if you also think about sort of the continuity of current del dot J, these have to close somewhere. And so you can see that there's sort of two currents. The lower latitude currents are going to be closing closer to the Earth, so sort of in the inner magnetosphere. And so they're often driven by some of these large gradients in the equatorial plane, both magnetic and plasma pressures, where the high latitude currents close on the magnetopause. So you have this supercoupled system, as Christine was showing with the Dungy cycle, but thinking about these connections, these field lines and field line currents are connecting to different regions in the magnetosphere. So a lot of generators, a lot of things are creating these flows. Great. Any other questions? I see just a lot of super awesomes and thank yous.
Thanks, guys. I'm glad to have the feedback that it was helpful.
Great. So we'll see everybody at the bottom of the hour for Slava Merkin's talk. Hi, Slava. Looks like we're getting a quorum. Just to check if folks can give me a thumbs up or show their faces. We're getting a good group. Nick, do you have any logistics to start?
Nope.
Great. So,
Okay.
Slava, please take it away. Introduce yourself and begin.
Okay, so I can start sharing my screen, right?
Yes.
And you guys can hear me okay and see me?
Yes, we can.
Okay, excellent. Yeah, I'm on travel in a hotel room, so the internet is hotel Wi-Fi. Hopefully it's going to go well. If you are having bandwidth issues, let me know. I'll turn off my video. But hopefully for now it's working well. So, hi everyone. My name is Slava Merkin, and I was very happy and honored to be invited to give you this lecture on magnetosphere modeling. I work at Johns Hopkins Applied Physics Lab. I'm a principal scientist there. Applied Physics Lab, just like Christine's employer, Aerospace, is a nonprofit that works, that does work for NASA, NSF, and other U.S. government agencies. And so APL's main business in space exploration is building missions and instruments. I work at a group that does basically scientific research in support of these missions, and more specifically, I lead a group at APL that does numerical modeling, computer modeling of the magnetosphere in this particular case. And so that's what I'll talk to you about today. All right, so we're gonna have two parts to this lecture, and let me say from the start that I really like to have these things go interactively. So if you have questions, feel free to just raise your hand or ask in the chat, and I'll try to address your questions as we go. And then hopefully in the end, I try to leave 10 minutes or so at the end for you folks to ask questions if you have any. Okay, so the two parts of the lecture, the way I structured it, is going to be first mostly about numerics and numerical methods, how we do what we do, and why we do it that way. And it's going to be mostly about magnetohydrodynamics. That's essentially hydrodynamics with the addition of magnetic field. So it's the numerical study, in this particular case, numerical MHD. It's a study of plasma flows and correspondingly how magnetic fields also participate in these flows. And then at the end, I'll also mention how we really need to go beyond MHD. Everybody realizes it. It's very hard because it's a very expensive computationally problem. but we are starting to do it now. And then the second part, I'll go more into the science or scientific application of these numerical models that we're building. And we'll talk about many things that Christine talked to you about, but now from the standpoint of numerical simulations. And I should be really, really grateful to the wonderful introduction that Christine gave, because that gives me a really great foundation to build on and talk to you about more sort of nitty-gritty details of these things. And then in the second part, I'll mention a couple of current cool projects that are just starting or have started. One of them is the Center for Geospatial Storms that you see the logo down at the bottom of the screen. Okay, so part one, why MHD? How to build a global MHD model. And I'll talk to you about some of the numerical details, like I said, and then I'll talk a little bit about what we, or we as a community, are doing to go beyond this plasma approximation. So to start, we really need to go to the beginning of space age and understand even why we are talking about applying these methods of magnetohydrodynamics to studying space plasmas, in this particular case, the Earth's magnetosphere. So it goes way back to some of the earliest papers that were written in this field. It was known at the time that space plasmas are collisionless. That means that we have very, very few particles per unit volume. And that means that particles don't really interact with each other by collisions. They do interact with each other because they're charged particles. They do interact with each other through electromagnetic fields, but they don't interact through collisions. And as you probably know from your coursework, you really need some sort of a collisional process to thermalize your distribution function and make it isotropic. And that's the approximation, an isotropic distribution function that lies at the foundation of hydrodynamics. And so people realized early on that magnetic field may play a role of this process that kind of ties particles together and maybe allows us to use fluid methods or magnetohydrodynamic methods to describe space plasmas. And so that's this comment, that's where this comment is coming from. Despite its weakness, the interplanetary magnetic field has the important effect of causing the solar wind to behave as a continuous fluid. And thus it seems that we should treat the interaction between the solar wind and the magnetosphere in terms of continuous or continuum flow rather than free molecular flow. So back at the time, it was really just a theoretical conjecture, but it led over many, many decades now to a very successful use of these magnetohydrodynamic or fluid methods in description of space plasmas. And in this particular case, description of the interaction of the collisionless solar wind plasma with the magnetosphere. And you can see here the sort of cartoonish descriptions or depictions of the of this interaction from that paper in '62, which still look very relevant even today. They are not very far from reality, so it's pretty incredible. So going a little bit again to the more fundamental plasma physics question, and I'm struggling to remove my Zoom window. Okay, this is better. From the just basic plasma physics point of view, Karlsruhe in this very excellent book said that even if for weak magnetic fields, in this particular case for space plasmas, the basically, because particles gyrate on a magnetic field kind of binds particles together, and that allows for a fluid description of collisionless plasmas. In fact, it's what is at the foundation of the guiding center description of plasma that Christine talked to you about. In reality, things are even more complicated than this, because magnetic field makes plasma what we call gyrotropic, but not necessarily isotropic. And so you need some sort of a wave process to isotropize the distribution function to make use of fluid equations. Unfortunately, in space plasmas, there are always waves that we believe are sufficient to isotropize the distribution function. Okay, so you've probably seen ideal MHD equations. That's on the left, and I kind of grayed out on the right a more complex set of equations that people use when you have more than one fluid and potentially different pressures. I'm not going to talk about that. I'm just showing it to you to give you a flavor of how much more complex things become if you start looking at different fluids. But even when you have the single fluid magnetohydrodynamics, these equations that you see on the left are actually extremely complicated. You see that they're very nonlinear, and so they lead to very complex, nonlinear, sometimes chaotic dynamics, which defines the interaction of the solar wind with the magnetosphere. The energy equation which you see here, E here is the plasma energy. You can see it down at the bottom. I don't know, do you see my mouse? Hopefully you see my mouse.
Yes.
Okay, I'll actually use a laser pointer. Okay, here we go. So the plasma energy consists of the kinetic energy and thermal energy here. So we can see that this equation here defines the evolution of the total plasma energy. And you can see how it's made of the divergence of the flow of what we call enthalpy, plasma enthalpy. It's the energy plus pressure. And also the work that the Lorentz force is doing. I will give you this excellent reference here where Joachim Bern and Michael Hesse are taking apart basically this equation and are looking at how different terms contribute to energy balance. It's a really superb paper that I really encourage you to read if you want to understand better, just analytically, and also they include some simulations, how different terms in this equation balance in the real plasma system. Okay, so now we're moving to more sort of numerical representation of these equations. And again, I need to remove the Zoom window. Okay, so what you see on the left is, I believe, the first ever MHD simulation of the Earth's magnetosphere. It was done, it's basically as old as I am, so not very young. And it was really a revolutionary contribution at the time, because like I said on my first slide, at the time it wasn't even clear that something like hydrodynamic equations should describe the interaction of the solar wind with the magnetosphere. However, if you look at these snapshots on the left, these are meridional plane cuts through the simulated magnetosphere. You'll realize that in reality today we know that magnetosphere doesn't really look like this. For example, the tail here is extremely short. In reality, it's much longer. And so around that time, people started realizing that when you simulate the magnetosphere interaction with the solar wind, you really need to do a very, very careful job at solving your equations numerically. And so this is very well said here in this quote from Lyon paper in 1980, who said that the magnetosphere contains a number of discontinuities. We now know that there is the bow shock, for example, and the contact discontinuity, which is the magnetopause. And the fact that these discontinuities exist means that they must be modeled as accurately as possible to retain the real physics of the situation. And so he then goes on to describe there is a numerical dilemma, which I'll talk to you about in the next slide. But this realization led to the realization that you need to do a very, very accurate job at solving your MHD equations numerically. That led to the development or application of methods that are called flux-corrected transport methods that we'll talk about in the next few slides. So application of those methods to the magnetosphere, and this led to another revolutionary paper. It's two papers in the 80s and in the 80 and 81 by John Lyon, who was and remains my good old friend and mentor. So it led to this set of revolutionary papers that applied these flux-corrected transport methods to the Earth's magnetosphere. And you can see that at the time, this was a 2D simulation, and it was fairly had fairly low resolution by modern standards, but it produced a much more realistic looking magnetosphere with a fairly extended magnetotail back in 81 already. Okay, so what is flux-corrected transport? I won't go into a lot of detail about this. I will give you, let me see. I want to put in the chat, there is an excellent book if you want to read it. It exists online in PDF. And then oops. Let me somehow don't, oh, here it is, chat, here. I lost the chat window. This is an excellent book. You can read it. It has some wonderful stories and anecdotes about how these methods came about. It was, in the 70s at NRL, they at the time weren't really interested in things like the magnetosphere, but they were interested in more military applications, the bomb and so forth. And so the development of these methods really at the time, it basically revolutionized the field of computational fluid dynamics. And as this book tells you, basically, essentially all of the computational fluid dynamics methods that are used today, you can trace them back to these original methods that Boris and Book revolutionized back at the time. But what is the problem? The problem is that even if you solve a linear advection equation numerically, it actually is an extremely, extremely difficult problem if you are dealing with something that has sharp jumps, sharp boundaries. So it's a very famous problem. You can actually try it yourself if you want to, take your language of choice, IDL, Python, MATLAB. I did it when I was a graduate student. Just try to code an advection of a step function like this. And if you do something very simple, first order method, you'll realize that very quickly after some number of cycles, here they show after 800 cycles or steps, it will turn into this, right? So you can't really preserve the shape of this sharp step function if you just use some simplistic numerical scheme to advect it. It will turn into this. In other words, you will have a very strong numerical diffusion. So what's the problem? Why can't we go to higher order methods? You know, we're essentially doing a Taylor expansion of this function and preserving some number of terms in that Taylor expansion. The more terms you preserve in your numerical scheme, the higher accuracy you should have. The problem is, as soon as you go beyond the first order, that numerical representation of your equations becomes dispersive. Dispersive means that you start introducing frequencies into your solution that are not there in the original solution. In other words, the solution becomes non-monotonic. So you create these spurious extrema, overshoots and undershoots. And so even though you tend to preserve the narrower shape of these sharp boundaries, you create these spurious extrema that basically lead to your solution breaking down. And so what the flux-corrected transport methods do, that again were revolutionized by, introduced and revolutionized the field of computational fluid dynamics by Boris and Book, they do this very interesting trick where they apply a scheme that is higher than first order, preferably much higher than first order, everywhere away from these sharp boundaries. And then only where they see sharp boundaries, they introduce just enough diffusion to kind of diffuse away these spurious peaks. And what I say sounds simple, but in fact, these are very complex algorithms, and there's a very large number of different algorithms that follow this general methodology. And again, you can open this book if you are into this kind of thing, and you'll read all about it. So some examples of applying these kind of methods to advecting various shapes, you can see that people actually, you know, a step function obviously is not the only thing that people want to advect when they solve real world problems. So you can see here advection of different shapes, a narrow Gaussian, a step function, a triangle, and sort of a more, it's not a Gaussian, it's, I forget what this function is, but all of them are equally difficult to advect, and you can see how this particular implementation, you can find it in that paper, does the advection of these different shapes. And again, I'm giving you some references here to the original papers where you can go and look for more details. Now, what's interesting is to compare what you get by applying different numerical methods to advecting these different shapes. And so what that's what this slide shows you. You see probably the simplest possible scheme, that numerical scheme that people still use today. It's called TVD, which is total variance diminishing. It means that it removes the spurious extrema, but it's still fairly low order. So you can see that there's high numerical diffusion. And then there are some other methods. PPM stands for a very popular method, parabolic piecewise method. We know method here, which is non-oscillatory. I forget what WE stands for. Also a very popular scheme, and something that we use in the code that we use and are developing in my group, which is called something which is called PDM, partial donor method. So this method was developed by John Lyon that I mentioned earlier, and you can see fairly complete description of it in this paper on JSTP. So what I've shown you so far were examples of one-dimensional advection, but obviously we solve problems in more than one dimension. And so what you're seeing here is a very nice, interesting problem, which is called the slotted cylinder test, where you take this shape, a slotted cylinder, and then just rotate around. In the example on the left, you see it rotating on a just simple Cartesian grid. In the examples on the right, you see a grid that is kind of warped curvilinear, which is shown by its boundaries here. This slide shows you another example of why, going back to this slide, why a higher order numerical scheme is important to use is because it allows you to preserve the original shape and the original jumps in your solution with a smaller number of cells. So as an example, here you see a two-dimensional representation of two schemes. One is a low order scheme that has a lot of cells, 1,000, basically 1,000 times 1,000. The other one is a very high order scheme that has 8 times less cells, fewer cells in each dimension. Sorry, jumped for me. Yes, 8 times fewer cells in each dimension, and you can see that with a fewer number of cells, it still very nicely preserves the original shape. And this plot here at the bottom shows you just a slice through this image, and you can see how nicely, if you have a high order scheme with a smaller number of cells, you essentially obtain the same solution than what you would have gotten with a lower order scheme, but much larger number of cells. Why is the number of cells important? It's important because the computational cost is essentially determined to a large extent by the number of cells that you're using. So if you can find a numerical method that solves the same equations with the same accuracy, but using fewer cells, you want to use that method because it will cost you less. And of course, because computational power is not infinite, at some point, if you are using a lower order scheme, you will basically run out of the computer power. Even the most powerful computer in the world might not be large enough to solve your problem. Okay, so I was talking to you about high order reconstruction. I won't go into detail about that, but the idea is fairly simple. If you have here a numerical scheme and you need to calculate some variable at any given point or an interface like this, basically the higher order scheme you use, the higher order reconstruction you use, the more cells on each side you're using to interpolate. It's essentially interpolation by using some number of surrounding points to a point of your interest. And the more points you use, the higher order scheme, the higher order reconstruction you have. Another way of demonstrating that you really want to use a higher order reconstruction is shown in this plot here, which just shows the number of, basically error as a function of number of cells, error of your calculation is the number of cells, function of the number of cells for different schemes. And you can see that even if the overall order of your scheme remains the same, and that's determined by the slope of this curve, of this line, if you use a higher order scheme, your overall error can be orders of magnitude smaller. So that's important to use higher order reconstruction. Another very important point to make here is since we're solving magnetohydrodynamic equations, we are dealing with the magnetic field, obviously not just plasma as a fluid. And magnetic fields are kind of pesky because they want to be solenoidal or divergenceless. And this tends to be a really, really significant problem in numerical magnetohydrodynamics, because if you're not careful enough, if you develop a numerical scheme that does not preserve solenoidality of the magnetic field or divergenceless of the magnetic field, you will end up with a basically with numerical artifacts that can produce unphysical solutions. So there are different ways to deal with this problem that people use. I'll tell you about one, which is called constrained transport. It's a method that relies on the so-called Yee mesh or Yee grid, which I'll describe to you in a second. But it was introduced in numerical MHD by Evans and Hawley in '88, and this is an extremely highly cited paper because this method is now used in essentially all of astrophysics and in some of the space physics simulations as well. So the idea here is actually beautifully simple. The idea is that if you have a numerical cell, you can develop a grid where your magnetic fields will be defined on the cell faces, like so. So the magnetic field is defined by for a cell, is defined by 3 variables, which are, or rather 6 variables if you take all of the faces, which thread the faces of this grid cell. If in addition to that, you define electric fields on the cell edges, then you realize that if that's the way you choose to do your discretization, then the magnetic field will remain solenoidal for the duration of the simulation, just because, as this equation here is showing, just because the magnetic field will be changed only by the circulation of the electric field around these edges, but because, and this is a very, it's beautiful and elegant. It's an example of using a numerical method that really bakes into itself the physics of the equations that you are solving. So going back to what I was saying, the change of this field BI, for example, will be determined by the circulation of the electric fields around this face, but the change of field BJ will be determined by the circulation of the electric field around this face. And you see how, in this particular case, this electric field EK along this edge comes into this calculation exactly twice, but in the different directions. So they cancel each other exactly. The contribution of this electric field to the change of magnetic field flux through the faces of the cell is exactly 0. So it's an extremely beautiful and elegant technique. All you need to do this way is just discretize your equations so that your different variables are defined in different places of your grid. Okay, so we've talked about the sort of basic MHD numerics, but we are in the business of solving these MHD equations for a realistic system, in our case, the magnetosphere. And so what do you need to do to go from basic MHD to global magnetosphere simulations? There are a number of considerations that you need to make. One consideration is the choice of the grid. There is an excellent tutorial by Jimmy Rader, one of the main people who have developed MHD codes for the magnetosphere. So if again, if this is something that you're interested in, I urge you to read this wonderful tutorial. You can also find it online, and it's a chapter in a book on numerical methods in space plasmas. All of that book in its entirety is online. You can find it, and this tutorial is a chapter in there. It's excellent. It was written almost 20 years ago, but it's still very relevant. And so you can use different types of grids to solve your simulations. You can use the simplest Cartesian grid, stretched Cartesian grid, and then you can do even curvilinear grids like these, unstructured like this, or so-called adapted mesh refinement, where you refine your grid in regions where you need more resolution. All of them have their own pros and cons. The simplest grid here, for example, is the simplest possible grid to program. The coding here is very simple, but it really gives you very few choices in terms of, for example, putting more resolution where you need it, because you basically are bound to having the same resolution everywhere. And so these grids tend to be extremely expensive if you want to do high resolution simulations. And so all of them have their pros and cons. The simulation that I'm using in my group and that we're developing is called Gamera. It's using a curvilinear grid that looks like this, and then you get three-dimensional representation by rotating this leaf essentially around the axis. So I'm just looking at the time, how much time I have. There are some additional considerations now that we've talked about grids. The boundary conditions. The external boundary condition, of course, is the solar wind. The problem with this boundary condition is that most of the time, we really have just one point, which is called L1 point. Probably heard about it in the maybe last week in the solar wind lectures. Here in this representation, you see the sun is over there, almost 100 million miles away from the sun is the L1 point, where we usually have one or a handful of spacecraft around that point that measure the solar wind. And then we are bound to driving our simulations with measurements of the spacecraft that's here upstream of the Earth, about 1 million miles. And so that immediately shows you that there's a problem, because we are using one point to drive a global three-dimensional simulation. So we need some tricks, and I'll talk to you about these tricks in a minute. But this just shows you an example of a typical input into our simulation. These are just solar wind measurements from L1, density, temperature, dynamic pressure, velocity, three components of the velocity and magnetic field. This is just this is not an input into the model, but this just shows you that this is a storm simulation that I showed here, VST of minus 150 nanotesla. But this is just an example of a typical input that we use to drive our simulation. So I hope you can see these notes that I jotted down on my notebook here. What are some of the caveats that you have when you drive a three-dimensional model with one-dimensional input? Well, one of the main caveats is, again, the problem of the divergence-less of the magnetic field. You have to keep the magnetic field divergence-less. So how do you do that if the only thing that you know about the magnetic field in this three-dimensional volume of the solar wind, represented here impacting the Earth and the magnetosphere, if the only thing that you know is your 1 point time series at this location here? So you have to make assumptions. So the assumption that people usually make is that the solar wind consists of these planar fronts. They can be tilted in some arbitrary way, but you have to assume that the solar wind consists of these planar fronts. and essentially all MHD models assume that one way or another. And the normal of this front cannot change in time. Now you'll see why it cannot change in time. So if you transform to the coordinate system that's aligned with the front, because we only have 1 point measurement, we have to assume something, and we assume that nothing changes within this planar front. So the variable, the derivatives with respect to variables, I call them y prime and z prime. Basically, they're variables in plane of the front. So the derivatives, you have to assume that they're 0 because you have to assume something. But you can then very quickly see that if you apply this equation star or 2 equation star to the divergence b equals 0 equation, you very quickly will realize that from that follows that the magnetic field component that is perpendicular to this front, bx prime, has to be constant in time. And then from that, you very quickly can derive that the x component in whatever coordinate system that you're using has to be a linear combination of y and z components. So that immediately gives you a very significant limitation to what you can input into your global model. You can't use all 3 components of the magnetic field. You can only use 2 of them as a function of time, y and z, and then the x component will have to be a linear combination of 3. And we usually do this by doing some simple linear regression where we essentially throw out the measured bx component and replace it with the linear combination that looks like this. Okay, so that was the external boundary condition. The internal boundary condition is the ionosphere. And this is something that I've dealt a great deal with. You can find some details in my paper with John Line in 2010. But the basic physics of this you can find in the Baum, Johann, and Troyman book in chapter 5.4. It's an excellent book. So at the inner boundary of our MHD simulations, what we do is if you take this as the inner boundary, you essentially map along the magnetic field to the ionosphere. You map the field line current to the ionosphere, and then in the ionosphere, you solve the current continuity. I'm deriving it here. For current continuity, what you do is you assume, you apply the so-called thin shell approximation to the ionosphere. You assume that the ionosphere here, these heights are very, very small. The difference between these 2 heights is very small relative to the height itself. And so then if you apply the divergence of the current equals 0 equation, you can then separate it into perpendicular divergence and horizontal, and field aligned, and then you integrate this equation star from H1 to H2. And as you do that, you then apply this assumption that I just mentioned, that the ionosphere is a thin shell, and then you can move the integral to inside the divergence operator, where you are integrating along the height the plasma conductivity, which we then call the height integrated conductivity. We call it conductance, and you end up with a 2-dimensional instead of 3-dimensional equation that looks like this. And then I'm looking at the time. How much time do I have? I have like 7 minutes, right?
That would be great.
Yeah. Okay. All right. I'll skip some of the material toward the end. But the point here is that in this equation, what we have is the field line current that the MHD code calculates here at its inner boundary, and we then map it along the field lines into the ionosphere. And then we need to assume something for the ionospheric conductance. And if we know that, as a two-dimensional distribution, then we can solve this equation numerically for the electric field. And that's what we do. This just gives you sort of a schematic, representation of this whole algorithm. You solve your MHD equations on a large magnetospheric grid like this. That gives you the field-aligned current in this equation. Then you use something for the conductance. For the conductance, we can use either semi-empirical models, or we can take it from models that solve ionosphere, thermosphere, mesosphere, ITM models. And I'll talk to you about that in the next couple of slides. And then you solve that equation numerically, you obtain the potential. And then if you know the potential, you can then find plasma velocity from the E cross B drift. And then this velocity becomes the boundary condition for your MHD simulation. So you can see how this is very, very complex business, even going from just using basic MHD numerics to applying it for a real world system like the Earth's magnetosphere interaction with the solar wind. So once you do all of that, you obtain a global MHD simulation. And as I mentioned, this started in essentially 40 years ago, in the late 70s, early 80s. At the time, they were doing two-dimensional simulations with this size of the grid. And this is from a relatively recent simulation that we're doing in our group. This is now three-dimensional with a lot more cells, as you can see, and a lot of dynamics in the magnetosphere, on the boundaries, everywhere. We'll talk about in the second part of the lecture. So just to give you a sense of, again, going kind of looping back to the point I was making, that you really want to have good quality numerical solutions and numerical scheme. It's not just for the matter of making nice pictures. Good numerics really gives you good physics. In this particular example, we used our code with very high resolution to solve, or hopefully advance, the problem of so-called auroral beads, which are these bead-like features in the aurora. This is looking from famous all-sky imager that Christina introduced to you, and this is from our simulation. You can see that even the highest resolution simulation that we could do, this was very expensive. We used 100,000 computer hours for each simulation hour here, so it was very expensive. And even with this, you can see that we barely started resolving these features, but we could connect them physically to a plasma instability in the magnetosphere equatorial plane. And it was nice, even Forbes picked up this paper. So I'm running out of time. I was gonna play this nice movie that NASA made about this, but you can hopefully look at the slides later and play it for yourself, or you can Google it. It's a very nice movie that NASA made here.
Right before.
Okay, I'm gonna move beyond that and just kind of introduce the next part of the lecture by saying that today we've moved way beyond just solving MHD equations for the global magnetosphere. Today, these global magnetosphere models are really coupled frameworks of different models that treat different parts of the system numerically. You can see that without going into detail, just conceptually, these are extremely complicated models. This is from the Jimmy Rader's group. This is from a project that was called CISM in the early 2000s. This is probably the most used model in the community, SWMF from University of Michigan. Also is a framework of coupled models. Something that we're developing, I'll talk to you about this in the next slide. We call it MAGE, next lecture, multi-scale atmosphere geospace environment, also a framework of different models I'll skip these two slides and I'll go to this, and I'll just say that today, not only are we using these coupled frameworks, we're also trying to go beyond the MHD approximation to description of space plasmas or magnetospheric plasmas. And there are a number of codes and projects in the community that are trying to go in that direction. I don't have time to go over each one of these, but this slide actually I took from an excellent tutorial that John Dorelli gave at the GEM workshop just 6 weeks ago or so. And it's online. You can find it at this link here, or just go to the GEM website and you'll find the tutorial. And he's describing these different methods and codes there, and they're all given with references if you're interested. So I think that's the end of the first part of the lecture, and I'm right on time. So
awesome, thank you very much. So feel free to raise your hand or unmute yourself or type in the chat. One question that I have, this slide sort of shows trying to incorporate some of the smaller scale physics into these global models. But which of the basic global assumptions for MHD modeling do you think is the weakest link? Is it the del.B BX issue at the dayside mapping, or is it the inner boundary assuming some conductance, or which one?
Yes,
would...
very good. Yeah, very good question, Mark. All of the above is a quick answer, but specifically these methods here, you know, even in these coupled frameworks that we're now using or keep developing, the backbone of the global magnetosphere description is still MHD most of the time. What these projects are doing here is trying to go beyond MHD for the backbone. And so going back to this slide here, this actually is a very good example. In that paper, we said, I think in the title even, we said, doing global simulations at the limit of MHD approximation. The problem is that we are doing the simulations now at such a high resolution that we're starting to enter the ion kinetic scales, particularly in the magnetotail. So, you know, this simulation had a resolution of about 300 kilometers in the central plasma sheet. That's essentially thermal ion gyro radius. And that means that we can't go further just by using MHD. We need to start including ion kinetic physics, and that's what these methods are doing. One way or another, all of them are starting to look at the physics that includes ion kinetics, be that in some way, be that whole MHD or global hybrid methods, or some of them are even trying to do a full particle in cell for global magnetosphere, or embedded in some sense. So to answer your question, I think it's ion kinetic physics is what is the next big challenge.
Great, and that I think addresses Pauline's question as well in the chat. And Pratik, go ahead and unmute yourself.
Yeah, hi. So I had one question regarding the isotropic nature in the MHD. So sometimes we know that there is not sufficient isotropy, is anisotropy, for example, T parallel, T perpendicular. So what will the effects if we include something like CGL method in MHD or versus only ideal MHD? So what will the differences that we will see in the final results?
So the short answer is we don't quite know, because I believe there's probably one paper from using SWMF from the University of Michigan that did that applied the CGL condition for anisotropic MHD. It's basically an area that remains largely unexplored, partly because CGL in real world doesn't really work as a closure scheme. You need to come up with some method of basically dealing with plasma instabilities that come into play when you go beyond isotropic approximation, like mirror instabilities, and you need to quench them somehow in order to avoid numerical instabilities. So in a sense, some or all of these methods that are listed here include plasma anisotropy implicitly or explicitly, because they just go beyond MHD, so beyond ideal MHD. Hopefully with the further development of these new global codes, we'll have better answers to your question.
Thanks.
One of your points on this slide, as we sort of go from peta, exa, and keep on doubling Moore's law, is there a tool that the higher education community could use, sort of like a Xbox game that I can take and have students run some of these modules, or still send to CCMC to run some of the big codes? Or
I think it's coming up. I don't think it exists now, but the big role here will play cloud computing, because you can imagine even now summer schools use Amazon Web Cloud or web services, for instance, for students to kind of fire up their instance and run a model or analyze it. So with the emergence of cloud services in these educational settings, and the GPUs, graphical, or more generally just I think they're called heterogeneous hardware, but more simplistically GPU. If you can, as we adapt our codes to run on GPUs, and then you can access a GPU or a number of GPUs through Amazon Cloud or something like that, the community and the student community will be getting more and more access to these simulations. So I think it doesn't exist today, but down the road, not in the very distant future, we will have these codes running efficiently on GPUs, and you will be able to access them on the cloud through CMC in particular.
yeah, I just bought my 90-year-old father a new iMac, which he uses essentially for email and the web, but it's eight core, the Apple M2 with 8 GPUs. It's like that's their standard thing now. So it's crazy. Any other questions? And Pauline, was your question answered, or do you want to follow up? Great, thanks. Okay. Nick, do you have any instructions?
Sure. Slava, do you need like a 5-minute break?
It can be 5, it can be 2.
Okay.
So we can start on time if you guys are okay with that. That would be what, 10:30?
Let's take a 3-minute break in case anybody who's hanging around needs to desperately use some facilities.
Okay, sounds good. We'll be back.
Okay.
Okay, so if you can, another thumbs up, just make sure we have a quorum. If you're around, or feel free to. We're getting. Okay. So go ahead and take control of the screen and begin with your second part.
Okay. So, second part of this lecture, like I said, we will be dealing with now applying these codes or numerical methods that we just discussed in the first part of the lecture to the actual simulations of the system. And I'll highlight some of the, I kind of tried to show you guys stuff that you won't find in textbooks. This is sort of recent research, but I tried obviously to kind of put it in a form that would be both interesting and accessible to not necessarily an expert in the field. So the first problem that we will be dealing with is convection or Dungy convection. And again, I should be very, very grateful to Christine for introducing all of the basics here so that I can, I have a very solid foundation for moving forward. We will talk about convection and what the form that convection takes that we think today in the real system, in the magnetosphere. And then we'll see if I have enough time. I'll talk about a couple of ongoing or new projects that are just cool. One of them is a project that I'm leading, and one is a NASA mission that's called EASY that is just taking off. And I'll see if there's time, I'll talk about that as well. Okay, so transport in the magnetosphere. When we say transport, we usually mean either particle transport or magnetic field transport, or usually it's both, because much of the particle distribution is frozen into the magnetic field, but not all of the time, not always. So on the left here, you see the classical picture of the Dungy convection that Christine has already introduced. So I won't go into details of that. So that's the transport of the magnetic flux in the cycle of life of the magnetosphere. On the right, you see again a classical picture of now particle transport. Particles further in the tail are E cross B drifting, frozen into the magnetic field and moving earthward. And as they are coming close to the Earth, they become more and more energized, just adiabatically. And as they acquire sufficient energy, they start exhibiting curvature gradient drifts, where ions will drift westward or toward the dusk side, and electrons will drift eastward or toward the dawn side. That's a classical picture of magnetic field and particle transport in the magnetosphere. However, and that's where the bubbles come in, and I'll use the word bubble a lot, maybe too much. But it turns out that a long time ago, it was shown theoretically by Ericsson and Wolf that seemingly steady convection in the magnetosphere shouldn't exist. The reason for that is because of the quantity that we call flux tube entropy. And flux tube entropy is basically P, where P is the pressure, and V is the flux tube volume, gamma is the polytropic index. So the flux tube volume here is defined as just the field line, an integral along the field line of 1 over B, where B is the strength of the magnetic field. It turns out that this flux tube entropy, this quantity, is a conserved quantity. It's an invariant of MHD equations. And you can read another excellent paper by Joachim Byrne that I'm giving here, where he derives it very, very nicely from the basic MHD equations and shows that the flux tube entropy should be constant as the flux tube is moving according to MHD equations. This turns out to have very significant implications for convection in the magnetosphere, because if the entropy of the flux tube should remain the same as it's moving from deeper in the tail toward the Earth, seemingly because it traverses all these different radial distances, seemingly the entropy in the tail should be the same, independent of the radial distance. However, number one, we know now, for example, from simulations that the entropy is increasing. I'll show you later some simulations of that. Entropy should be increasing away from the Earth, but also even in this earlier work by Erickson and Wolf, they showed that if you assume entropy conservation, then if you take a typical flux tube deep in the tail and convect it inward, preserving flux tube entropy, you will end up with pressure in the inner magnetosphere that is just way too unrealistic. It's too high. And so that created this conundrum. How does convection even happen in the magnetosphere when seemingly it violates basically the equations of MHD? Later on, in the early 90s, a breakthrough came from observations. This was early papers using geotail spacecraft by Baum-Johann and Angelopoulos. They observed that the convection in the tail occurs to a large extent. To what extent is actually still kind of under debate, but to a large extent occurs in the form of these bursty flows. They're bursty in time, and at the time they didn't know this, but now we think that they are also localized in local time and space, in the cross-tail direction, in other words. And so they are bursts. They were observed as being bursts. Now we call them bursty bulk flows, or BBFs, of hundreds of kilometers per second. They are typically dipolarizing. In other words, they bring increased magnetic field inward from the tail earthward. That's why they're called, also later they started being called, these magnetic field structures, dipolarizing flux bundles. I think Christine also mentioned them. And later, people like Rumi Nakamura here used the cluster spacecraft, which had 4 spacecraft separated by a few RE or so, to estimate cross-tail size of these bursty bulk flows, and concluded that they were in this range, from 1 to a few RE. So why am I talking about this in this context of entropy? Is because we now believe, and from a lot of simulation work, but also infer from observations, that these bursty bulk flows or dipolarizing flux bundles, they are also flux tubes that are depleted of entropy, of flux tube entropy. And that, we believe today, may be a solution to this problem that Erickson and Wolf put out in the early 90s, in the early 80s, in the sense that the low entropy bubbles, as they're created in the tail, presumably by reconnection, and I'll tell you about that in a second, they want to move from deep in the tail toward the reservoir of low entropy that exists near Earth. And I'll show you some very visual representations of that. But before I do that, let me just show you this picture here from Joachim Byrne that demonstrates in a very, very neat way how or why we believe reconnection creates low entropy flux tubes, it's essentially a geometric effect. If you go from a flux tube that's long like this, and then you cut it, just by cutting a significant portion of the flux tube, you're decreasing its overall volume. And then from this equation, you'll just get these red flux tubes here that have much lower entropy than they had originally. This here is a movie from a simulation that we did in this paper. This is by Karim Sarafi, who works closely with me. So this is a simulation using MHD, a global MHD code. What you see here is an equatorial slice of the magnetosphere, and what's shown is in color is the flux tube entropy. And so here you see this reservoir of low entropy. It's low because the magnetic field is very large. It's a dipole field near Earth. And if I go back to this formula, you'll see that other things being equal, forgetting about the pressure for a second, if you have a very large magnetic field, the flux tube volume will be small. And that's basically what you're seeing here. So entropy tends to increase away from the Earth, but reconnection that is happening further out here keeps creating these low entropy flux tubes that Dick Wolf called bubbles, and now we're all calling them bubbles for that reason, is exactly because of the analogy with the bubbles of air. These bubbles are also buoyant. They're just buoyant in a different sense. They're buoyant magnetically rather than gravitationally. And if you want to learn about that, you can read any textbook on interchange and stability in plasmas, and you'll see what magnetic buoyancy means. But you can see how they're kind of raising to the top in a sense. They're trying to move toward low entropy. So this is I believe a nice schematic that Christine already showed. This is from paper by Dubagin in 2011 that kind of envisioned how a low entropy bubble, if you look at the profile of the flux tube entropy in the magnetotail, this is just increasing radial distance, and this is flux tube entropy. It's increasing away from the Earth, as you can see here on the right-hand side. But if you somehow created the bubble, and again, we believe that it's created by reconnection, this bubble will want to move to the point of equilibrium where its entropy is the same as the entropy of the background. And so it will want to move earthward. And so today we believe that, again, much of the transport of the magnetic field and of plasma in the magnetotail occurs this way. It occurs in the form of these bursty flows and entropy bubbles. The remaining question that the community is struggling with is, to what extent? What is the role? What is the relative role of sort of more uniform background convection versus this bursty, azimuthally localized, or mesoscale, as we call it, convection? So why is it important, other than just being potentially a solution to the pressure catastrophe, or this conundrum that Erickson and Wolf formulated? Well, it's important for many, many reasons. They're listed here. Number one, this mesoscale transport is important for moving magnetic flux. So it's fundamentally, it's the Dungy cycle that we were talking about earlier. It also is important for bringing particles into the inner magnetosphere, into the ring current and radiation belts. So it's important for storm time physics, which cannot exist without ring current and radiation belts, which are obviously extremely important space weather concern. They also are important. I mean, this mesoscale transport is also important for creating various wave populations, scattering particles, and creating precipitation and coupling to the ionosphere through field line currents. So one thing I want to emphasize here is the sort of global perspective. And let me go to this picture here and try to describe what I mean by that in more detail here. So if we believe, let's kind of walk through this diagram from right to left. If we believe that this mesoscale transport is important for building up the ring current, then it really has global implications for the entire geospace system, not just the magnetosphere, because if this mesoscale transport is important for building up the ring current, which is still, like I said, an open question. To what extent is it important? To what extent does it contribute to ring current formation? But if the contribution is significant, then the buildup of the ring current has effects in the ionosphere, because it creates these region 2 field line currents. By the way, this is not a cartoon. This is from an empirical reconstruction of the magnetic field in the magnetosphere from real magnetometer, historical magnetometer measurements. So you can see these blankets here are sort of blue and red. Here are the representation of region 1 currents that are at higher latitudes, and these are region 2 currents that are closing or coupled to the field line current, and to the partial ring current that flows here near the equatorial plane. And so if you have a strong ring current, it closes through the ionosphere through region 2 currents, and region 2 currents close through the electrojets in the ionosphere to region 1 currents. And so that in and of itself is already a global effect, but even going beyond that, the closure of these region 1 and region 2 currents occurs across the electrojets. Now moving to the left side of this picture, this here shows a Joule heating, just collisional heating in the ionosphere thermosphere system. So basically, electrojets is where energy is input into the ionosphere thermosphere, and ions and neutrals, because ions and neutrals are coupled, even the neutral atmosphere is disturbed through neutral winds, which in and of itself then creates a global redistribution during strong storms, redistribution in the thermosphere, which affects the ionosphere and feeds back onto the magnetosphere. So you can see how you start with these mesoscale flows in the tail, seemingly, they're relatively small compared to the global system, but their global effects through the buildup of the ring current and effects in the ionosphere thermosphere can be, their effects can be truly global in the entire geospace system. And so Mark asked me to mention the CGS, one of the drive centers. This was the problem that I was just mentioning to you, was one of the underlying ideas behind this center that we proposed and recently were lucky to be selected, one of the 3. It's a large scale, very large scale grand challenge type of a project that goes after processes and coupling feedback loops, like we were just talking about. The one that I was talking to you about in the previous slide is one of the topics that we're addressing in this center. And just for the educational point I want to make, we run basically annual workshops. We've had 2 so far in the past 2 years, which have quite a few recordings, Zoom recordings of experts in the field giving tutorials or talks on this topic and also other topics that you can just go to this website and listen to the Zoom recordings. Some of them are very, very good from the educational standpoint. So going back to why this mesoscale transport or convection is important, we talked a little bit about the magnetic field, and I'll talk about it later as well. This here shows you effects on particles. So why are these mesoscale flow channels important for particle transport and energization? People talk about two mechanisms. One is sort of more of a classical picture where you see here what we call a convection surge. Even if it's localized in the azimuthal direction, you can see here the sort of convection finger moving toward Earth. If you have a particle that is inside of this convection surge, it will be moving earthward due to the E cross B drift. And as it's moving, it's also accelerating because the magnetic field is increasing as you move earthward. And so for as long as it stays inside of this convection channel, it will be accelerated adiabatically. An even more efficient and kind of more interesting mechanism was discussed in a number of papers, including Christine's papers. And so she talked about this, I think, a little bit in her lecture, but also there's a lot of simulation work that points to that. It's the so-called magnetic trapping idea. And you can kind of see it here illustrated in a cartoonish way, but here this is a real simulation that we did in our group, where you see in the background the magnetic field structure is shown, and you can see that these dipolarizing flux bundles they're like magnetic islands. So the contours of constant magnetic field are kind of closed on themselves, and so if you're a particle that is exhibiting magnetic gradient drift, it will be moving around this island basically, and that creates a very efficient mechanism for particle trapping. So these particles, as you can see in this movie, they're just trapped inside the island as the background plasma flow brings this island toward the inner magnetosphere, and that's how at least some people believe particles are accelerated into the inner magnetosphere and then populate. In this particular case, this is, I believe, ions, so they would be creating the ring current, the ion ring current, and the electrons would be injected into the radiation belts in the same way. Let me see, there's, I believe, a question in the chat. So good question. I don't believe this works in the, so the question is, does this mechanism work in the magnetic field in the F region in the ionosphere? If the question is about the particle energization, I don't believe so, because the magnetic field doesn't really change that much. It's, to zeroth order, it's just dipole. So you really need to move particles from low magnetic field strength to high magnetic field strength to accelerate them adiabatically. I don't know if I answered the question. Feel free to let me know in the chat. All right, let's assume that I addressed it. Okay, and then there's another question. So in the same area, the question about plasma bubble, does it have a relationship between this phenomenon and the plasma bubbles which occur in the equatorial F region? So this is a very, very good question. So I'm not an expert on ionospheric physics. From what I know, people believe that equatorial plasma bubbles are created by Rayleigh-Taylor instability, which is it's sort of a subset or a branch of a more general plasma interchange instability. So the Rayleigh-Taylor instability is created by or is the buoyancy that's responsible for it is gravitational buoyancy. The buoyancy, like I said, that's responsible for the motion of these plasma bubbles in the magnetosphere is magnetic buoyancy. But with that part aside, they are buoyant, and it's really the question of whether it's gravitational force that creates this restoring force or returning force, or a magnetic force. But other than that, mathematically, you could even describe it in the same way, just replacing gravity with the magnetic pressure. So in that sense, they're not the same, but they're very similar. Okay, so moving on to now magnetic field transport. I believe again, Christine probably talked about that a little bit. Let me see if there is a, yeah, great. So why do we think this mesoscale transport is important for global magnetospheric dynamics? Here we are talking about magnetic field or magnetic flux transport. So again, going back to the very quintessential question of Dungy cycle in the magnetosphere. You need this magnetic flux circulation to make Dungy cycle works, to make Dungy cycle work, and that's how we believe it's happening in the form of these bursty flows. So on the right, you see a simulation that we did in 2019. You can see how magnetic flux is, the background here is the magnetic flux in the, or magnetic field in the equatorial plane, and you can see how it's happening in terms of these localized magnetic field dipolarizations. If you look at how much flux this dipolarization bring magnetic flux they bring to the inner magnetosphere, that is what's shown in this plot here. It's kind of a tricky space-time plot. So what we did here was we just took a ring around the Earth at some distance here, 8 RE, and plotted the magnetic field along that ring as a function of time. And you can see here, so in the center of this plot is midnight, toward the sides is the day side, so we're not concerned with the day side for now. But you can see that around midnight, the magnetic field at 8 RE in that particular simulation, and it was a realistic substorm simulation, is coming in the form of these localized bursts, so to speak, and they accumulate with time in sort of an avalanche manner, so that you build up the magnetic flux over time at this radial distance just by accumulating these localized flows. And in that paper, we showed that not only was this mechanism sufficient to explain the essentially all of the flux circulation in the magnetosphere, and it was consistent with observations. So not only was it sufficient to explain the observations, also the entirety of magnetic flux transport in the inner magnetosphere was provided by these localized magnetic field bursts. And this wasn't the only simulation that did this. There were similar simulations by the group that used OpenGGCM model, and they had very similar conclusions. That said, and I believe I'll talk about this in the next few slides, this is one of the greatest challenges that we as a community face today. This kind of circles back to the last slide in the first lecture that I had. These processes, this mesoscale magnetic transport, is really getting to the point where MHD approximation is not going to be sufficient, just because again, as we call these structures, they're mesoscale. So they're small enough that they're kind of bridging the scales of where fluid approximation is applicable or useful, but also ion kinetics becomes important. So we really, as a community, need to start developing methods that in one way or another include ion kinetic effects in these global models. And so this slide kind of talks about some of these ion kinetic effects and some of the global models that are starting to come online today. So this is a plot from the ULIN group in Auburn in Alabama. They use a global hybrid code which treats ions in a magnetosphere as kinetic particles, and so they also show these bursty flows, and they include an isotropic pressure, going back to the question that was asked earlier, and they also they show how these bursty flows generate kinetic alpine waves that themselves have effect on particle dynamics and scattering and so forth. But the problem is these codes are still extremely computationally demanding. Let me see, there's a question in the chat. Yeah, so I believe that's basically what I was just saying. Observationally, people believe that around these bubbles there are kinetic waves that scatter and accelerate particles that we see in particular in the ionosphere. This is very active area of research today. So very good question. And that's partly the reason why we need these codes that go beyond MHD to investigate effects of waves and instabilities that are created around these bubbles on the particle populations. And so this example here shows you temperature and anisotropy in these bubbles, T parallel versus T perp, in one of these simulations. The problem that we have today is that these simulations are still extremely expensive. So you know, we really can have only either relatively low resolution simulations, or running them for relatively short periods of time that we can afford with today with the supercomputers that exist today. But this is, you know, these methods of including ion kinetic physics into your global simulation is definitely where the future lies for global modeling of the magnetosphere. Okay, so one of the examples here of how important but also challenging it is, and you can see here two MHD simulations that are only different in their resolution. Other things are completely the same, and then we threw a large ensemble of test particles on top of these MHD simulations, and we looked at how they contribute to the ring current formation. And so you can see that just if you look at the background color here, which is the magnetic field in the equatorial plane, they might not look very different to you. However, if you look at particle dynamics, you'll realize that only the high resolution simulation traps particles sufficiently well that the injection into the ring current is sufficiently efficient. And so essentially you need to have a high enough resolution simulation to create a ring current particles. And that kind of goes back to the point that I was just making, which is even with MHD simulations, to have sufficient resolution to capture particle dynamics in terms of even test particles, these simulations are extremely expensive, even just for MHD. So doing simulations that go beyond MHD physics and test particles creates an extremely challenging problem. And this is a problem that I just mentioned answering Mark's question at the end of the previous lecture, which is when we run these MHD simulations at high enough resolution, we, so to speak, run out of runway in the MHD sense, because we start pushing the spatial scales where really ion kinetic physics should be important. So this is a slide for you guys for the new generation of space physicists. I asked my close colleague Karim Sarathia to create the slide, and he likes dogs very much, so that's why the dogs are here. But the point here is that the challenges that we have today are opportunities for you, for the next generation. It's an extremely complex landscape to navigate. We're dealing with extremely complex algorithmically and coupled frameworks rather than sort of single simple models. The hardware that we're dealing with is increasingly exotic. You know, hardware is essentially heterogeneous. You have CPUs, you have GPUs. They're connected by complex and fast interconnect networks. We are dealing with a landscape where we hopefully will get more and more observational data to constrain or assimilate, even assimilate in our models. And so we need a new generation that will know how to work with these massive, both simulation and observational data sets, and apply hopefully methods of data analytics that are also coming into this field explosively. And so this is a great time to be a modeler, not just because we have challenges for you guys, but also because, you know, sometimes we have great examples of people who have acquired sufficient skills working in this area, and then unfortunately to us, but maybe sometimes fortunately to them, found very lucrative tech jobs. And so being a modeler in this field today is a really, really great opportunity. So I invite you all to become strong modelers or data analysts with dealing with these massive data sets. And so I'll just say this briefly. There are opportunities today. This is an opportunities that are existing within our center. What's relevant to you is probably graduate, or to your friends, graduate student opportunities that we have within our universities. So you know, pass on the word, or if you're interested, you can contact either me or one of these professors and let us know. And this will be going on for 5 years. So hopefully, maybe when you graduate, there will be opportunities that we will have. All right, so in the last few minutes, I wanted to talk a little bit about the sort of the effects of these mesoscale flows in the tail in the ionosphere. Something also Christine kind of touched upon a little bit, and so I'll kind of pick up from there. So what you see here is a sort of a cartoonish view, but based on a real simulation that we did. you can see here this bursty bulk flow penetrating from the tail into the inner magnetosphere. What's shown here in these field lines, they're magnetic field lines, but they're colored by the field line current. And you can see that they're twisted. These flux bundles are kind of twisted such that the field line current goes into the ionosphere on the eastward side of the penetrating flow and out of the ionosphere on the westward side. And so when this current, they call it a wedgelet, right? It looks like a wedge, but it's relatively small scale compared to the global size of the magnetosphere, so we call them wedgelets. So this wedgelet creates a localized current closure region in the ionosphere, like a current blob that you can see here. And so there are outstanding questions about how much do these wedgelets contribute to the global current closure in the ionosphere, and also what effects do they have maybe on the ground, as we see them in ground magnetic field. This should just to kind of emphasize the point that I keep making throughout this presentation, is that we really need high resolution models to study these phenomena, because in low resolution models we simply don't capture these processes. So these 3 plots here show you the precipitating electron flux. So it's kind of a proxy for aurora, looking down on the North Pole. Noon or sun is at the top, and you can just see 3 simulations of progressively higher resolution going from left to right, doubling resolution every time, and you can see how you get these very dynamic and very localized auroral features, which are actually observed as streamers and some other things like torches and omega bands in the ionosphere. So, interestingly enough, something that many people don't realize is that we don't necessarily see these structures very well on the ground for a number of reasons, not just because you need sufficiently dense network of ground magnetometers, but also because the size of these features in the ionosphere is about 100 kilometers, and that's also the distance from the current closure region in the ionosphere, which is the E layer, to the ground. So just by Biot-Savart law, the contribution of these features kind of washes away as you get closer and closer to the ground. So what I'm showing here is from the high resolution simulation that I was showing on the previous slide. I'm showing magnetic perturbations resulting from the ionospheric currents at 2 different altitudes, and these are just 3 different components: azimuthal, zonal or north-south component, and radial. And so I'm showing them at 100 kilometers and 0, meaning on the ground. And you can see how this localized structure kind of gets washed away as you get to the ground. Sometimes you can still see it, it's just weaker. Sometimes it may disappear entirely. And so that was the motivation behind this very nice mission that NASA is currently implementing, or I should say APL is implementing for NASA. It's called Electrojet Zeeman Imaging Explorer. It's basically 3 CubeSats that use the same techniques that we use, essentially the same techniques that we use to measure magnetic fields on the sun, but they use to remotely sense the electrical currents and magnetic fields in the ionosphere. And so what this will do, hopefully, in the end, is going back to that MHD simulation that I was showing to you earlier. As one of these spacecraft flows over the ionospheric footprint of these bursty flows in the magnetotail, it will see something like this structure moving underneath. This is actually these are magnetic perturbations that are reconstructed from a simulation like this, not this exact simulation, but from a simulation like this. And so the spacecraft will have, each of the 3 spacecraft will have 4 beams like this, kind of measuring the magnetic field along 4 tracks and reconstructing the maps, 2-dimensional maps of electrical currents. So this is really cool technique, observational technique in measuring the magnetic field. So in the interest of time, let me, just looking at the time here. Yeah, so let me skip one of the questions that hopefully this mission will address is this question of wedgelets that I was mentioning to you earlier. How much do these current wedgelets contribute to the global current closure in the ionosphere? And a nice way to visualize it is to look at these waterfalls. Basically, you can move the same amount of water through the waterfall either by using this uniform large-scale flow, which we call substorm current wedge, substorm current wedge, or you can have it happen in multiple wedgelets, like some people believe, as shown in this diagram, and then it will be a waterfall like this. So it's this dichotomy between these 2 scenarios is what simulations like what we do and missions like this Mission Easy will hopefully address. So let me skip through this and go to my last slide, which is really getting to the question of how do we use data and models to move the field forward. We are really getting to the point with this mesoscale physics that we've been discussing. As a field, we have gotten to the point where, as some people say, our models far surpassed the ability of existing data sets to validate them, right? So our models show these very structured, bursty, localized flows that have global effects. They are important for creating ring current. They're important for moving the magnetic flux through the system. They have important implications in the ionosphere thermosphere system. But we really don't have observations to validate this modeling picture. And so we really need not only new types of observations, but also new methods of kind of combining models and data together in this joint pursuit of understanding, a deeper understanding. And so the answer to this will be, the answer to this problem will obviously be heterogeneous, if you will. We need missions that will have many spacecraft. You can see here studies like this from Drew Turner relatively recently use sort of fortuitous alignments of spacecraft that we have there. But even if you have a fortuitous alignment like during this event, we still really have just a handful of points in the magnetosphere. So we hopefully in the future we'll have constellations, large constellations of many spacecraft that will be there all of the time. We need new methods of auroral and ENA. I don't know if you guys have talked about this, but this ENA stands for
energetic
neutral
yeah.
atoms. Yeah.
Yeah.
Yes, thank you. I forgot what E stands for. Energetic neutral atoms. Yes. So these are methods of imaging the magnetosphere. like is shown here, using the existing TWINS satellite. But hopefully we can get to better resolution with the next generation missions. And finally, like I said, we should, with more and more data to analyze and more elaborate models that we have, we need methods of modern data analytics, data mining, machine learning, information theory to analyze both observation and simulation data sets together in this joint pursuit of understanding. And ultimately, the question is, will we learn the same thing from models and data? And if we don't, then we need to adapt our models and develop them further. So I'll stop here. This is my last slide, and see if we have any questions.
Thank you very much. Please do ask questions, take advantage of the opportunity, even if it's going to tell them that you're going to send your CV over to them for a postdoc. You can show your face, and so he knows where you're coming from. So the astronomers have developed this idea of multi-messenger, looking at multiple wavelengths, combining different views of the same astrophysical observatory. And we're sort of doing that with the Heliophysics System Observatory. But do you know of anyone sort of doing it thoughtfully, trying to figure out what observations would best leverage superdarn and incoherent scatter and all sky imaging with easy type of remote sensing, or of is anybody sort of thinking more grand that you know of in terms of developing not only large number of spacecraft, but what's the appropriate type of observations to combine the remote sensing and in situ?
Yeah, so specifically with the data sets that you're mentioning, there is a project that Tomoko Mutsuo at Colorado University is pushing, which is called, or developing, which is called MGO. And that is a technique, it's an assimilative technique that combines these different data sets together to create a sort of global multivariate solution for ionospheric electrodynamics. I believe, let me put it in the chat, but they have a nice website that you can check. MGO is
Great.
the name of the project, but ultimately it will be assimilative techniques, I'm sure. I don't know of anything like this happening with magnetospheric data sets, partly probably because they are so disparate and we still have so few points. But that said, I want to mention that this technique here that I actually have on the slide is using methods that are kind of in the same family as machine learning and data mining to so they use historical data sets of magnetic measurements, specifically magnetometers in the magnetosphere, to create a global reconstruction of the magnetic field at any given time. And they used to do it for just storms. This is sort of new generation of Stepanenko type models, but they have been doing this more recently for even substorms. And for example, I believe it might have been in this paper. It's almost unbelievably realistic in terms of, for example, capturing the X lines that MMS observes. I think they're capturing with this method, I forget, something like 90% or more of MMS observed X lines. So, even with existing data, just using historical data that may have millions and millions of data points, people are able to create this sort of global reconstructions using modern methods of data analytics.
Great. And there's a couple of questions. One, Andrea, do you want to unmute?
So first off, Slava, thank you so much for this interesting talk. This was super neat. I'm especially interested in the magnetic bubbles that you were talking about. I know you had said that they form by magnetic reconnection. I'm curious if there's another way to form magnetic bubbles, particularly at a planet that does not have a global dipole intrinsic magnetic field, but perhaps at Mars, where you have an induced magnetic field. I'm wondering if this type of phenomenon can exist, and if so, what the formation mechanism would be. As far as I know, I don't think that we've observed magnetic reconnection at Mars as of yet.
Yeah, so it's a very, very good and keen question, and thank you for the kind words. The reason we believe that reconnection is responsible is because these bubbles are intrinsically unstable, right? So people believe that you need to have some sort of a non-MHD process to create them, because MHD on its own, how would you create something that's intrinsically unstable? So people believe that that's where they're coming from. That said, if you can find ways of kind of channeling free energy in the system to move the your plasma and magnetic field into a non-equilibrium unstable state, then this is possible. I'm not sure about Mars. In the Earth's magnetosphere, some of the methods people discuss are basically well, actually, you still need to create dayside reconnection for that. So I take it back. the only method I know is reconnection. is what I can tell you. It's some people talk about the magnetic flux evacuation theory that Otto and co-workers have put forward. Magnetic flux evacuation. I'm just typing it in the chat. I don't have the reference handy, but you can just Google it. So the idea basically is that you kind of, by dayside reconnection, you're removing flux from the inner edge of the plasma sheet on the night side, and you can, so just by kind of sucking flux out of the magnetosphere, you can create unstable configurations on the tail. So but one way or another, you either need to create them through night side reconnection or through dayside reconnection. That's at least what we know, or what we believe today, because nobody have thought about anything else.
And these are similar to the discussion around, is there a Dungy cycle for the heliosphere? And one of the difficulties is you have a supersonic flow going out. So it's not a lot coming into the inner magnetosphere in terms of this cycling of magnetic flux. And so similarly, I would imagine for induced magnetospheres, there's probably there's reconnection and stuff going out, but not a lot coming back. But it's something that definitely, in terms of entropy bubbles and low density or changing the topology of that flux tube or the size of it, seems to require reconnection. But there is another question from Pauline. Do you want to clarify in what type of models you're referring?
Oh, I was talking about just MHD models in general, like Gamera or LFM or SWMF, how we normally use a dipole as Earth's magnetic field. And do you think it's worth trying to put in something a little bit more realistic? It's not a huge change, but I I'm just curious. I wonder if it would make any difference in some of our predictions.
Yes, absolutely. Very good question. I fully agree, except it depends on how far you want to go with this. It may not be a small change. The question is, again, what exactly are the effects of non-dipole effects that you're interested in? But we are working, for example, on including IGRF field, which is the sort of the background model that is obviously more realistic than the dipole. If you go away from the Earth, we're working with a graduate student at Johns Hopkins who's doing this for Mercury. Mercury internal magnetic field is very non-dipolar, and it has an offset due to quadrupolar terms. But going back to Earth, yes, this is very important, both for just basic physics, north-south asymmetry, hemispheric asymmetries, and for example, radiation belt effects, lost cone size, things of that sort. So very important to start including them in our models. And I see there's another question: does these models, are they able to obtain upwelling and downwelling of different species from and to the ionosphere? So yes, this is also a very good question. We have some models like SWMF and our model that include kind of outflow physics. That said, these are the physics of outflow, upwelling, downwelling, and if upwelling is sufficiently strong, leading to outflow into the magnetosphere, the physics of that is still poorly understood, even at Earth. And so this is a very, very active area of research, and there is a lot of room for new work.
Do you want to briefly explain the origin of the name of your new model with your flying turtle?
Well, I guess I'm trying to remember. So John Lyon, who was, I mentioned it in the previous lecture, who is a great, brilliant mind and a mentor. He turns out to be a kaiju aficionado, so he loves the old kaiju movies. And so I don't know if people know what kaiju are. And my earpods are running out of juice. Let me switch to the internal.
Can you still hear me, guys?
Yes. We can hear you.
Can you hear me?
Yes,
Okay.
we can.
Yeah, sorry, my earpods ran out. Earpads. So yeah, I don't know how many people know about the kaiju movies, but there are, the old Japanese movies about imagined made-up monsters. Godzilla is one of them. There's like it's a whole cultural phenomenon. And so he loves those movies, and that's where this came from, and that is a constant source of joy in our group because there are a lot of jokes that are going around.
Did you make a nice acronym out of it?
Oh yes, we call it the backronym. It stands for Grid Agnostic MHD for Extended Research Applications. So say totally very meaningful acronym.
Great.
I think that's a that's a new type of scientific training we need to do is how to make up find a good word and then fit the acronym to it. Right?
Oh yeah,
Oh,
yeah.
definitely.
It's amazing how many NASA mission names are invented that way.
You, Slava, you had a plea in the middle of your talk to recruiting people who want to get into modeling, and what so what's a good entry into that? It's into the, I mean, these are large, sometimes legacy codes that you would seem daunting to try and start from scratch or find a way into it.
Yeah, so this is it's a great question, Nick. We unfortunately don't have a good setup for this in this community, but we have a great example in other communities, for example, astrophysical community. So I would encourage folks to take courses in applied math or computer science departments, learn how to code well, code fast, learn numerical methods, and then, as you're coming into the field, you will not be intimidated by all these complex codes. Sometimes frankly, if they're legacy codes, most likely they need to be rewritten because they won't run on modern architecture. That's part of the reason we took LFM and turned it into Gamera, which essentially was not essentially, it was a full rewrite. We left the algorithms in, but we rewrote the code completely from scratch because LFM had great algorithms based on these FCT methods that I talked about in the very beginning, but it was a code that wouldn't run on modern architectures. So, and it took somebody who came from astrophysics, actually, Karim Sorathia, to do this. And so if you like this type of work while you're a graduate student, try to take courses, try to learn how to code and code for these new architectures.
Great. Sounds like we need a white paper for the decadal survey on this.
I believe there is actually one. At least that's what I've heard.
Okay, calling for it. Okay. I think we're well into the office hours at this point in time. There's another question in the chat, but I wanted to say that I think our program time is done for today. Is that a good call, Mark? Okay, Mark's giving me a thumbs up. And there's one short reading assignment. Matt's our lecturers for tomorrow have asked that you take a look at chapter 2 in the text and just familiarize yourself with that portion of with ions and a little bit about scale heights and atmospheres. So other than that, I think our program time is done. There's still a so Slava's starting to answer it in chat, but maybe he can speak to any other questions that you have for Slava, and if not, we'll see you tomorrow.
Okay.
Dr. Merkin, I was going to ask, I'm more on the heliospheric side of things, but I was looking through the different postdoc opportunities at Johns Hopkins, and who would be the contact person for the Parker Solar Probe and the Solar Orbiter opportunity?
So, well, there's. Is there an opportunity for a Parker probe? If there is, it's not mine, but I'll give you the contact. Noor Rao. I think I spelled his name correctly. Is the Parker probe principal? Project scientist.
All right, perfect. Thank
so
you.
yeah, just find his email. It should be online, and email him.
Great. Thank you very much again, Slava. Any
Sure,
other
thank you.
questions?
So just to follow up on Pauline's question, although it looks like she left already, just the difference between LFM and Gamera. I mean, you have to write the code to fit the architecture, and so that the compiler knows what to do with it. Right? Is that?
Yeah, so that's what Gamera was or is. It was written specifically in a way that would make it not just run on current architectures, but kind of envision and foresee future heterogeneous architectures, things like GPUs and accelerators and stuff like that.
All right. Any other questions or comments for Slava?
I misspelled his name, so here's his email. Found it.
Great. And Maggie, do you need anything from Slava in terms of a release form or slides?
Nope, I don't think so. He sent me everything that I needed.
Yay.
So thank you.
Thanks.
Yeah.
And you're in Seattle right now?
Yep, I'm in Seattle for the TESS
So
meeting.
thank you very much for taking part of your day away.
Oh, no worries, no worries. Thank you. It was fun and hopefully useful. If not, by the way, feel free to email me, guys, if you have any questions or need anything.
Thank you. So Nick, I think we're exhausted questions.
I think so. Yes, I think we're
Okay.
done for today. So.